Hi. In this chapter, we will be talking about the chemical nature of atoms, what atoms are made up of. Now, in the previous chapter, we talked about the various hierarchies in the biosphere, and we stopped at the molecular level. Now, we will go a step below the molecular level, which is the atomic level. And let's explore the structure of atoms, what they are made up of, and how chemical bonds such as the covalent bond and ionic bond form between atoms, which basically make up everything that we see around us, whether it is living cells or non-living entities. They're all made of atoms, right? So let's explore the atomic structure and learn about the chemical bonds. So as you can see here, the ants are spewing formic acid. So this is a type of acid that is produced in the abdomens of the ants. Now, this formic acid is very similar to the formic acid that is produced in lab. This just goes to show how important it is to understand the chemical nature of the cells, or how important it is to understand the basic chemistry and the basic chemical processes to understand or to extrapolate that understanding into understanding the various reactions that happen in living cells. So here we come to something called as matter. Matter is anything that takes up space and has some mass, right? Like, for example, air. Air is something that takes up space, right? And it also has mass. Why does it have mass? That's because it is made up of atoms, and atoms are form of matter, right? So air is matter, the dirt is matter, rocks are matter. Anything that you see around you that is tangible is matter, is made up of atoms. But if you think of light, light is not matter. It is not made of atoms. It is just a form of energy. So you wouldn't consider light as matter. And for that matter, even sound is a form of energy. So you don't consider sound also as matter, right? All these forms of energies, like, say, for example, gravity, which is another form of, or it's basically force, right? So it is a physical aspect. It's not something that is made of atoms. So we do not consider gravity as matter either. So all matter is made of either elements or compounds. Now, elements are the purest form of a substance, of matter, right? You cannot break it down into different substances through a chemical reaction. Like, say, for example, you take the pencil lead, and it's made of carbon. It's just the purest form of carbon, right? It's the elemental form of carbon. So if you break it down further and further, all you get is still carbon. You cannot make something different or new from it through a chemical reaction. Whereas a compound is a substance that is made of two or more elements in a fixed ratio. Now, that is very important. Like, say, for example, you have water. Water is a compound. It is made of 2 atoms of hydrogen and 1 atom of oxygen. That's the fixed ratio. Now, if you change the ratio of water, like, say, of the hydrogen and oxygen, like, say, you have 2 hydrogens and 2 oxygens, even though it's the same elements, it does not make water molecules. It is a molecule of hydrogen peroxide, right? So the fixed ratio is very, very important. Now, the number of elements that are found in a compound could be different, right? So compounds are made of 2 or more elements in a fixed ratio. And another important thing to remember is the compound has a different property. In this chapter, we will be talking made up of. In this chapter, we will be talking about the chemical nature of atoms, what atoms are made up of. Now, in the previous chapter, we talked about the various hierarchies in the biosphere, and we stopped at the molecular level. Now, we will go a step below the molecular level, which is the atomic level. And let's explore the structure of atoms, what they are made up of, and how chemical bonds such as the covalent bond and ionic bond form between atoms, which basically make up everything that we see around us, whether it is living cells or non-living entities. They're all made of atoms, right? So let's explore the atomic structure and learn about the chemical bonds. So as you can see here, the ants are spewing formic acid. So this is a type of acid that is produced in the abdomens of the ants. Now this formic acid is very similar to the formic acid that is produced in lab. This just goes to show how important it is to understand the chemical nature of the cells, or how important it is to understand the basic chemistry and the basic chemical processes to understand or to extrapolate that understanding into understanding the various reactions that happen in living cells. So here we come to something called as matter. Matter is anything that takes up space and has some mass, right? Like for example, air. Air is something that takes up space, right? And it also has mass. Why does it have mass? That's because it is made up of atoms, and atoms are form of matter, right? So air is matter, the dirt is matter, rocks are matter. Anything that you see around you that is tangible is matter, is made up of atoms. But if you think of light, light is not matter. It is not made of atoms. It is just a form of energy. So you wouldn't consider light as matter. And for that matter, even sound is a form of energy. So you don't consider sound also as matter, right? All these forms of energies, like say, for example, gravity, which is another form of, or it's basically force, right? So it is a physical aspect. It's not something that is made of atoms. So we do not consider gravity as matter either. So all matter is made of either elements or compounds. Now, elements are the purest form of a substance, of matter, right? You cannot break it down into different substances through a chemical reaction. Like say, for example, you take the pencil lead, and it's made of carbon. It's just the purest form of carbon, right? It's the elemental form of carbon. So if you break it down further and further, all you get is still carbon. You cannot make something different or new from it through a chemical reaction. Whereas a compound is a substance that is made of two or more elements in a fixed ratio. Now that is very important. Like say, for example, you have water. Water is a compound. It is made of two atoms of hydrogen and one atom of oxygen. that's the fixed ratio. Now, if you change the ratio of water, like say of the hydrogen and oxygen, like say you have 2 hydrogens and 2 oxygens, even though it's the same elements, it does not make water molecules. It is a molecule of hydrogen peroxide, right? So the fixed ratio is very, very important. Now, the number of elements that are found in a compound could be different, right? So compounds are made of 2 or more elements in a fixed ratio. And another important thing to remember is the compound has a different property, both physical and chemical, as compared to the elements from which it was made. Like say, for example, here you have NaCl or sodium chloride, also known as table salt. And we know that it is edible. It is form of pretty much everything we eat. And it is made up of 2 elements, the sodium, which is a metal, and it is highly explosive, and then chlorine, which is a poisonous gas, right? So these 2 extremely reactive and toxic substances, when combined in the ratio of 1:1, you have an edible sodium chloride. So that's how different the properties of a compound are compared to the properties of the elements from which it is made. So there are several different elements in nature. There are about 92 naturally existing elements, and there are several others that are made, also known as man-made elements. But out of all of these elements, now if you look at your periodic table in the textbook, you will see that there are several elements, but the elements that we are interested in this course would be carbon, hydrogen, oxygen, and nitrogen. We will be referring to these elements again and again throughout the semester. So 96, now the reason for that is 96% of living matter is made of these 4 elements, right? And the remaining are made of calcium, phosphorus, potassium, sulfur, and there are some other elements known as trace elements, which are required in very, very small quantities, such as iron or magnesium, manganese, zinc. All of these are, or iodine, right? These are essential. These are required for normal health, but too much would cause several side effects. Right? So that's the reason these are considered as trace elements. So these are required in very, very minute quantities. So our focus in this chapter would be the 4 elements, the 4 key elements that you would find in any living cell: oxygen, carbon, hydrogen, and nitrogen. So each element has unique atoms. Now, how are these atoms unique? When we are calling all of those atoms, how are they unique? They are unique because they have different numbers of subatomic particles. So an atom is made up of several subatomic particles, and the atom is considered as the smallest unit of matter that has all the properties of an element. Like say, if there is, like, we'll go back to the carbon element. Now, if you are able to separate individual atoms of your pencil lead, which is basically made of a bunch of carbon atoms, each of those atoms would represent or would have the same exact properties as the element carbon. So we consider atoms as the elements, the basic unit of elements. And all atoms are made up of several subatomic particles, but we will be talking about these 3 subatomic particles in this chapter: neutrons, protons, and electrons. Each of these has specific significance with relation to the atoms and how they function or how they interact with other atoms. So neutrons, like the name suggests, it has no electric charge, but it does have a considerable mass. Protons also have a considerable mass, and they have a positive charge. So P positive, that's one way to remember. And then the other one is electrons. Now, electrons are the most important, and we will be focusing on electrons for the formation of chemical bonds. So electrons have a negative charge, but they do not have a significant mass. They do have some mass, which is why we consider them as matter, but they do not have a significant mass. So it's usually ignored or not counted. The mass of electrons is not counted when we are trying to figure out the mass of an atom. We just add up the masses of all the neutrons, the masses of all the protons, because these two subatomic particles have a significant mass, right? And the mass is so small that even the smallest metric unit would be too big to measure the mass of these subatomic particles. So we use a special unit called as the Dalton. So the neutrons and the protons each have a mass of 1 Dalton. So the way these subatomic particles are arranged in an atom is the neutrons and the protons together form the core of the atom, and we call that as the nucleus. Now, this nucleus is different from the nucleus of a cell. But in general, the word nucleus means the core, right? The center. So in the center of each atom, we have a cluster of neutrons and protons, right? And then the electrons would form a cloud around the nucleus. And this cloud would be a cloud of negative charge because electrons have a negative charge. And the nucleus would obviously have a net charge of positive because neutrons are neutral, protons are positive. So the overall charge on the nucleus is positive, and right around the nucleus we have a cloud of negative charge that is made of electrons. So you can imagine this arrangement as the arrangement of planets around the sun. So if you consider the nucleus to be the sun, the planets that revolve around the sun would be the electrons. Here you see an example. Now, this is an atom of helium. Now, you don't have to memorize any atomic numbers, atomic masses. I will be providing you that with that information for the quizzes and for the tests. But what you need to know is how to arrange a given number of protons, neutrons, and electrons in an atom. Right? There are certain rules, and that's what we'll be going over in the next part of this chapter. So here you see the core. Right? You see the core of the nucleus, which is made of the positive charges, which represent the protons, and the brown circles represent the neutrons that are neutral. So that's the nucleus, and around the nucleus you see a cloud of negative charges. Now here, this is an illustration, the next one, with kind of like an orbit around the nucleus with 2 electrons in that orbit, each with a negative charge. Right? So every atom has 2 numbers associated with it. Now, if you open your textbook and you go to the periodic table, you will notice that every element has a certain symbol. Like for carbon, we use the letter C. Oxygen, we use the letter O. For sodium, we don't use the letter S. That is already taken up by sulfur. So we use another set of letters, Na, for sodium. So, I mean, again, you don't have to memorize any of the information in the periodic table, but just letting you know that the first letter of the element need not always be the symbol, right? So here, these 2 numbers, and every symbol or every letter has 2 numbers associated with it. So of the 2 numbers, the bigger one is called the atomic mass. The smaller number is called the atomic number. Now, the atomic number is very, very important for an element. It is kind of like the ID of that element, just like we have our social security number, right? It's kind of like that. It's unique to every element. Like say, for example, you have oxygen, its atomic number is 8, and no other element on the periodic table has that atomic number. Atomic masses sometimes may be the same for some elements, but the atomic number is unique. Okay? And this atomic number also gives you some information about the subatomic particles. So if I have oxygen and with an atomic number of 8, this also means that each atom of oxygen has 8 protons, and it also has 8 electrons. So 2 out of the 3 subatomic particles information can be derived from this atomic number. So the atomic number is equal to the number of protons, and it is also equal to the number of electrons. Now, moving on to the next number, which is the larger number of the two. That's called the mass number or atomic mass. And the mass of an atom is nothing but the sum of all the protons and sum of all the neutrons, because these two are the two subatomic particles that have a significant mass, right? Each with a Dalton. That's the unit. So oxygen, say for example, you will see the atomic mass as 16. Now what does that mean? What it means is if you have 8 protons in oxygen and the mass is 16, right? The mass is made up of 8 units of protons, and the remaining would be the neutrons, right? So the neutron number is always equal to the mass number minus the atomic number, right? So just with these two numbers, you can derive the number of neutrons, the number of electrons, number of protons, but you need both of these numbers.
These are 5 atoms that are important in living things. These are 5 atoms that are important in living things. The nucleus of each atom has a characteristic number of protons, which are positively charged, and neutrons, which are electrically neutral. Each atom of a particular element has the same unique number of protons. This is the element's atomic number. The number of particles in the nucleus, protons plus neutrons, is called the mass number. Most elements have 2 or more isotopes whose atoms vary a bit in neutron number and mass number. These are 5 atoms that are important.
Okay, now moving on to the next concept, which is isotopes. Now we said of the 3 subatomic particles, the proton number can never change. If it changes, it's like the ID, because your atomic number is equal to the number of protons. And the number of protons is constant for each element. So for oxygen, if the proton number is 8, for any oxygen atom from any source, the proton number would be 8. But the electron number can change. And when electron number changes, the result is ions. When the neutron number changes, the result is isotopes. Okay? When the proton number changes, it's a completely different element. So you have to know these 3 important things about what happens when each of the subatomic particles change. Right? Neutron number changes in an element, they become isotopes. Proton number changes, it becomes a different element. Electron number changes, it becomes an ion, right? So isotopes are different forms of the same element that have different number of neutrons, right? So the different number of neutrons is reflected on the atomic mass, because the atomic mass is made of neutrons and protons together. Right? And we said protons never change. The number of protons doesn't change. So when the neutron number changes, the effect would be seen on the mass number. So you can define isotopes also as different forms of an element that have different mass numbers. Right? So the isotopes have several practical applications, especially in the medical field. That's because isotopes, because they have these additional neutrons, they are very unstable and they tend to give off those extra neutrons. And as they radiate those extra neutrons, they also give off a lot of energy, and that energy can be captured as light. And that's what is used in some of these PET scan and CT scanners, and also these X-rays, radio active tracers. They are used for tracking the atoms in different metabolic processes, like say how did scientists even figure out the path of cellular respiration, path of electrons in cellular respiration, it was basically through radioactive isotopes. So they just followed the radioactive isotopes. So let's say, for example, they used oxygen that was radioactively labeled, then you just follow that radioactively labeled oxygen throughout the process. And you would figure out how or what various steps are there in, say, the process of cellular respiration. Right? And another practical use of radioactive isotopes is the radiometric dating, which is basically used in figuring out the age of various fossils that could be discovered. So this gives you an idea of when various life forms evolved, or how long ago the dinosaurs, like we know how long ago the last dinosaurs walked on this planet, like 65 million years ago. So how did scientists figure that out? So again, that's because of the radioactive isotopes, because the radioactive isotopes, they degrade at a fixed rate. That's called the half-life, which means how long it takes for a certain amount of isotope to be reduced to half the amount. So there's never, the radioactive isotope is never zero, right? It's always half and half and half, and zero is not a half of anything. So let's say, for example, we start off with 10 micrograms of carbon, a radioactive form of carbon, and then it takes about 1,000 years for that 10 micrograms to become 5 micrograms. Another 1,000 years would take for that 5 micrograms to become 2.5 micrograms. That's called half-life. So once you figure out how much of that radioactive carbon is left in the fossils, and knowing how much each species starts off with, because we all have radioactive isotopes. So once you know that, how much you started off with and how much is left, you can calculate how many half-lives have formed, have been completed. Add up all those years and you have the approximate age of the fossil. Right? So that's a very, very important tool in evolutionary biology or in paleontology. Now coming back to the atoms and the atomic structure. Now we just finished talking about the protons and the neutrons and their significance. And then we also talked about the isotopes, which are basically different forms of the same element that have different neutron number or different mass numbers. Now, the next thing we're going to be talking about, at least for the rest of this chapter, is the electrons. Now, the electrons are, at the beginning, we saw how they are arranged. They are arranged around the nucleus. And the electrons stay close to the nucleus because of the opposite charges. The nucleus has a positive charge, the electrons have a negative charge. Right? Now, these electrons don't just move in a random manner around the nucleus. They are arranged in a specific pattern, right? At a specific distance from, or a fixed distance from the nucleus. That's called as the energy level, right? Or it's also called as the electron shell, right? So each electron shell represents a certain amount of energy possessed by the electrons, right? So all electrons have some amount of potential energy. And based on how much energy they have, they are arranged or they are located at a certain distance from the nucleus, right? So all electrons do not have the same amount of potential energy. The ones that have the lowest amount of potential energy are the ones that are the closest to the nucleus. And as you move farther and farther away from the nucleus, you will see that the electron has more and more energy. So the potential energy of, say, the electrons in the third shell is more compared to the potential energy of an electron found in the second shell, which would be more than the potential energy found in the electron in, say, electron shell number 1. Right? So as you move farther away from the nucleus, the amount of energy increases. Right? So you can think of these as fixed steps, right? So here you have the nucleus, and then you have the first shell, the second shell, the third shell. It's kind of like, you know, the seating in the arena, right? You have these different rows, correct? And see how much there's a fixed amount of energy that is needed to move an electron, let's say, from the first shell to the second shell. So it has to gain energy. Now, how does it gain energy? It can absorb energy from the surroundings in the form of heat, in the form of light, right? And once it gets enough energy to move to the next shell, the electron can move to the next shell, right? So out of these three shells, the electrons in the third shell would have the highest amount of energy. Okay. So here, this is a little section of the periodic table in your book. And you see various elements here. You have hydrogen, and the hydrogen has the number 1 next to it. Now, you just have one number seen here because this number is the atomic number, right? And from this point onwards, we just need the atomic number, right? Because the atomic number tells us how many electrons there are in an atom, right? And once we know the atomic number, we can say, like say for hydrogen, it is 1, which means it has one single electron. And then the next element here, you see on the right side, it's helium, and it has 2 next to it, which means its atomic number is 2, and therefore it has 2 electrons. And also, of course, it has 2 protons, right? And so here, as you see, there are rows and columns in a periodic table. Now, as you go from top to bottom in a column, you will see that there is an additional electron shell added, right? And as you go in the rows from the left to the right, you will see that there is an additional electron being added. The electron number increases, or the atomic number increases by 1, right? So here in the leftmost element in the second row, it's called lithium, right? And it has the atomic number of 3, which means it has 3 electrons. And see how the 3 electrons are placed here? There are 2 electrons in the first shell, and then the next shell has 1 electron, the remaining 1 electron. So, and if you notice, for every element, for every atom in this row, there are only 2 electrons in the first shell, right? Which is basically the capacity of the first shell. So the first shell can only accommodate 2 electrons, right? And the next shell has, now if you go to the third row, you will see that they all have 3 shells. Now, why do we need 3 shells? That's because there are more electrons in each of these atoms, and that cannot be accommodated in the first and in the second. So you need a third shell. So what is the maximum capacity of the second shell? It is 8. Okay, 8 electrons in the second shell. That's the maximum capacity. Okay, so the first is 2, the second is 8. Okay, and then the third is actually 18, but for the sake of biology, we will just say 8. So these are the 3 numbers you need to memorize. Then you need to remember, right? 2 in the first shell, 8 in the second shell, 8 in the third shell. Now, why do we have to do this? That's because if I give you the atomic number of an element, you should be able to draw the atomic structure like the one shown here, right? The nucleus in the center with the protons and neutrons, and then you have the first shell with a maximum of 2 electrons. The remaining electrons go to the next shell, and the second shell can accommodate 8. And if there are any more electrons left, you would put them in the third shell, which also has a maximum capacity of 8, right? So this is the electron numbers, the capacity of electron shells, right? So if there is a certain element that has a certain number of electrons, and if that electron shell is not completed, like say for example here you have hydrogen. Hydrogen has 1 electron. Now what did we say the capacity of the first electron shell is? It is 2, right? So it is falling short by 1 electron, right? So what does that mean? It means that hydrogen is not going to be stable because it has an electron missing, right? It has an incomplete electron shell. So it's trying to look for that additional electron, which makes hydrogen atoms extremely reactive. If you move on to helium here on the right side, you will see that helium has an atomic number of 2, which means it has 2 electrons, and the capacity of the first shell is 2 electrons. So helium is happy, and it does not have to interact or go through any chemical reactions to get more electrons. It has what it needs to complete its electron shell, which is 2 for the first one. Now, if you see lithium here, lithium has 3 as the atomic number, so 3 electrons. 2 electrons go in the first shell, and there's that 1 electron in the second shell. Now, we said the maximum capacity of the second shell is 8. It has only 1, right? Now, there are 2 ways to have a completed electron shell, outermost electron shell. One way for lithium is, one option is to find 7 electrons and put them in the second shell. That's one. The other one is just give up that 1 single electron in the second shell, erase the second shell completely, and now it has the first shell, which is complete, right? So the easier way to do that is to give up that 1 single electron and have the first shell as the completed shell, right? And move on to sodium here, the next row. You have sodium with 11 electrons. So it has 2 in the first, 8 in the second, which is 10 electrons, and there is 1 electron in the third. Again, sodium has the same issue. It either needs to find 7 electrons to complete its third shell, or give up that 1 electron in the third shell and call the second shell as its outermost shell. Right? So that's exactly what these elements would readily do. Hydrogen would just give up its lone electron. So it has no electrons. So all that is left in hydrogen would be a proton, right, in the nucleus. Lithium, it also gives up the single electron in the second shell, and now it has a completed outer shell. Same thing with sodium. It's going to give up its single electron, and now it has a completed second shell. Now, as you move further and further to the right, now, say for example, you have oxygen here, right? Oxygen with 8 as the atomic number has 2 electrons in the first shell. That is completed. Then we move on to the next shell, and it has 6 more electrons left. So those 6 electrons are placed in the second shell. And we also said that the second shell has a capacity of 8. But oxygen has only 6. So it is falling short by 2, right? So it is going to look for 2 electrons so that it can fill up its outermost shell, right? So that's how oxygen is going to react. It's not going to give up its electrons because it's easier to find 2 electrons than give up 6 electrons. Now, fluorine has 7 in the outermost, so it needs just 1. So it readily picks up an electron rather than give up 7 electrons. So let's say lithium has given up its 1 single electron, right? That can be accepted by fluorine, right? So what you have just seen here is a transfer of electron, right? So what charge do electrons have? They have a negative charge, right? So when lithium with an atomic number of 3, which means it has 3 protons, each with a positive charge. So it has 3 positive charges and 3 electrons, therefore 3 negative charges. But now it has given up 1 electron. So now it is left with 3 protons or 3 positive charges and only 2 electrons or 2 negative charges, which means it has 1 additional positive charge. So now it is no longer neutral, it is charged. It has a positive charge of 1. Which means it is an ion, right? Now, in the beginning, we said when electron number changes, the result is electrons. The result is ions, okay? So here, fluorine, on the other hand, has 9 electrons, 9 protons, so the positive and negative charges cancel out. But once it takes up an electron from lithium, it has 10 electrons and only 9 protons, which means it has 1 extra negative charge. So the fluorine is also now charged, or it is now an ion. So the electron shell that is most significant that we have been talking about now, like, having a completed outermost shell, the outermost shell also has a specific name. It's called the valence shell. So the valence shell has to be completed. Only then the atoms become stable. They always look for a completed valence shell, okay? So all the electrons that are in a valence shell or the outermost electron shell are also known as valence electrons. Now, before we go on to the chemical bonds, There's one more thing to talk about, which is called the orbitals. Orbitals are basically the space around the nucleus where the electrons are found 90% of the time. Right? It's kind of like the house of the electron. Right? And each orbital, there are several different types of orbitals. Whatever type of orbital it is, it always has a capacity of two electrons. So an orbital can hold 2 electrons. And now what exactly are these orbitals? How do they relate to the electron shells that we've been talking about so far? The orbitals are basically sections of an electron shell. So every electron shell is made of one or more of orbitals, right? One or more orbitals. Like, say, for example, the first shell here, you see, it has one orbital. And how many electrons does an orbital hold, did we say? 2. And that's the reason why the first shell has a capacity of 2 electrons. That's because all it has is one orbital, which is kind of spherical. What does the shape signify? It's basically the path. Now, if I were to follow an electron in this orbital for some time, I would end up tracing a sphere or a circle, right? So it is just a path. It represents the path of electrons. Okay. So the first electron shell has one orbital. It's also called as 1s. The second shell has an s orbital, which is called as 2s. 2 represents the shell number. And then in addition to that s shell, there are these 3 shells. Now this is made of 3 different types of orbitals. They're called as p orbitals. The p orbitals have a different shape, like you can see here. It's like the number 8, right? The number 8 and then number 8. So all these 3 are in 3 different directions. And again, we said no matter what shape the orbital has, it always has a capacity of 2 electrons. And we have 3 of these p orbitals, each with a capacity of 2 electrons. Now add up all the electrons that could be accommodated in the second shell. 2 in the s shell, 2 in each of these 3 p shells, right? So that's a total of 6 and 2, 8. And that's what we said earlier when we were trying to fill out the electron shells. 8 is the maximum capacity of the second shell. Right? So here we're going to be now talking about the first type of chemical bond, okay, which is called as the covalent bond. Now what exactly is a chemical bond? A chemical bond results when atoms share or transfer one or more electrons, okay, with other atoms. So it could be a result of sharing an electron or a pair of electrons or several electrons between 2 atoms, or it could result, a chemical bond could result due to transfer of electrons, like we saw earlier how an electron was transferred from lithium to fluorine, right? So in that process, what happened was the lithium ended up with a positive charge, fluorine ended up with a negative charge, and because they have opposite charges, they stick together, and that's a chemical bond. So it's just the attractive force. It's not something that you can see, right? Like, can you see gravity? But it is a force that's keeping us on the floor, on the ground, right? So the first type of bond that we'll be talking about is a covalent bond. A covalent bond is a result of sharing a pair of valence electrons by 2 atoms, right? So it's always, the sharing always happens in pairs. So in how does that pair of electrons form? When each of the atoms involved in this sharing process contributes 1 electron each, right? So now you have a pair shared between the 2, right? So here, now if you remember the periodic table, we talked about hydrogen, right? Where there's a single electron in each of the hydrogen atoms in the first shell. So one way for hydrogen to become stable would be to give up its electron. The other way is if it contributed that single electron and another hydrogen also contributed to a single electron, that would bring them closer, like here, and then they would be so close together their electron clouds will literally overlap. And each of the hydrogen would then have that pair of electrons closer to the nucleus. just let me show you here in this. Okay. So when two atoms share a pair of electrons or more than a pair of electrons, they stick together, and that attractive force is called a covalent bond. So when more than one atom combines, it's a molecule now. So now you have a molecule. And for every pair of electrons shared, a single bond is formed. So when you see a double bond, like two lines between two atoms, it means that they are sharing two pairs of electrons. There are a few. Okay. So you can see how these molecules are formed. So we had this hydrogen with a single electron and another hydrogen with another one of its electrons. See how close together these are so that their electron clouds actually overlap. So now you have two electrons that are close to or equidistant from the nucleus of each of these hydrogens, right? So to do that, they each had to contribute one electron to form a pair of shared electrons. That is represented by a line between the two hydrogens. And this is what we call as the molecule of hydrogen. A molecule of hydrogen is made of two atoms of hydrogen. Now in the oxygen, so this is the oxygen that we actually breathe. It is the molecular form. We do not breathe individual oxygen atoms. Individual oxygen atoms, again, are very unstable. So what they do is they share electrons with another oxygen and form a molecule of oxygen. And this is the form of oxygen we breathe. So oxygen has 6 electrons in its valence shell. That means it needs 2 more, right? So it combines with another oxygen atom that also needs 2 electrons to complete its valence shell. So when these 2 atoms of oxygen come together, they end up sharing 2 pairs. So each of them contributes 2 electrons, making 2 pairs of shared electrons, which means they have 2 lines between them or 2 covalent bonds between them. That results in a molecule of oxygen with 2 atoms of oxygen. And then here you have water, right? It's a universal solvent. Now, each water molecule has 1 oxygen, 2 hydrogens. Now, the oxygen needs 2 electrons. If it is getting both these electrons from another oxygen, the result is a molecule of oxygen. But if the oxygen is sharing 1 electron each with 2 different hydrogen atoms, because remember, hydrogen needs 1. So it's going to contribute 1 and it's going to make a pair of electrons or share a pair of electrons with whatever atom it is pairing up. So here you have oxygen contributing 1 electron and hydrogen contributing the other. So that's 1 shared pair. And here oxygen is contributing 1 electron, hydrogen another electron. So a second shared pair. So this would mean that you would have an oxygen forming a covalent bond with 1 hydrogen and another covalent bond with a second hydrogen. And that would make a molecule of water, right? And here, finally, you have a molecule of methane. Methane has 1 central carbon. Now, the carbon has 6 electrons in total. 2 of them go in the first shell. It has 4 more electrons that end up in the valence shell, right? So it needs 4 more to complete the second shell. So the carbon can combine with several different elements in order to complete its valence shell, right? But here in this example, it is sharing a pair of electrons with 4 different hydrogens. So this is the structure of methane, a central carbon sharing a pair of electrons with 4 different hydrogens, right? So sharing of electrons results in covalent bonds, right? So in each of these examples, you saw that there are a fixed number of bonds formed, right? Like oxygen, whether it is for bonding with another oxygen or it is bonding with hydrogens, it is always going to share 2 pairs of electrons, right? So you would always see 2 lines radiating from oxygen atom. That's called the bonding capacity of oxygen. Now hydrogen, no matter where you find hydrogen, you will always see one line radiating from hydrogen, which means it is always going to share one pair of electrons, or that's the bonding capacity, right? Nitrogen has 3, so that's called the bonding capacity. So the bonding capacity is also known as the valency of the atom, right? And it is always the number of electrons that the atom needs to complete its valence shell. So that's the bonding capacity. Now we said hydrogen needs 1 more, so it's always going to form 1 bond. Oxygen needs 2 electrons, so it's always going to form 2 covalent bonds. Carbon needs 4, so it's always going to form 4. So that's the bonding capacity. And nitrogen needs 3 because it has 5 electrons in its outermost shell. So it needs 3. Now these are the 4 numbers you need to remember, the bonding capacity of these 4 elements, right? Hydrogen 1, oxygen 2, nitrogen 3, carbon 4. So at this point of the chapter, we will talk about a very important concept, and you will be using this concept to understand much more complex processes later on in the semester. So electronegativity is the atom's attraction for electrons. So this is kind of like a force, like a magnet attracting, say, some iron objects. So it's the same thing, but all elements have some sort of or some level of electronegativity, but they are all different. The amount of electronegativity or the attractive force that an atom has is different for each element, and this depends on various factors, especially the number of protons that are in the nucleus, because the higher the positive charge in the nucleus, the greater the electronegativity would be towards the electrons. So if you look at the periodic table, the electronegativity increases as you move from the left towards the right. Okay? And as you go from the top of a column, also known as a group of elements, towards the bottom of the group, the electronegativity decreases. So when you're talking about electronegativity, you do not include the rightmost column, also known as the noble gases, such as helium, neon, argon, and so on. So based on how the electronegativity changes across and down the periodic table, fluorine is considered as the most electronegative element in nature. Now, as far as living cells are considered, oxygen, which is right next to fluorine, that would be the most electronegative element in living cells. So this is something that you need to remember about the high electronegativity of oxygen, that is the high affinity of oxygen for electrons. And this is the reason why oxygen is used in cellular respiration. So when we get to that point, you will actually see how important the role of oxygen is in cellular respiration. Okay? So based on this electronegativity, you will see that the covalent bond, which is a result of sharing of electrons, this kind of a covalent bond is going to be different based on the electronegativities of atoms. So let's say, for example, now as far as electronegativity is concerned, you need to know the relative electronegativities of the 4 elements that we are going to be talking about throughout the semester, which is oxygen, nitrogen, carbon, and hydrogen. So on the electronegativity scale, these 4 elements stand in this order. So you have oxygen at the very top, with being the most electronegative element, and right behind oxygen is nitrogen. Okay, the second most electronegative element in living cells, and then all the way at the bottom of the scale of electronegativity would be carbon and hydrogen. Now, what does this mean in terms of the nature of the covalent bond? Now, let's say, for example, if you have 2 atoms with different electronegativities or different affinities for electrons are combined through a covalent bond, right? So when does a covalent bond form? It forms when the 2 atoms are sharing 1 or more pairs of electrons. Now, if these two atoms that are sharing the electrons have different electronegativities, the atom that has a higher electronegativity will have a greater pull or force with which it's going to pull the electrons towards itself. So at this point, what happens is the electrons that are supposed to be shared equally are no longer shared equally, right? So since the electrons have a negative charge, whichever atom is pulling the electrons closer to itself will end up with a slight negative charge. And the other atom that is losing this tug of war for electrons will end up with a slight positive charge. So basically what happened here is, instead of sharing the electrons equally, the electrons are displaced closer to the more electronegative atom, right? And this resulted in certain charges, or it creates polarity in the molecule. And therefore, this covalent bond is called as a polar covalent bond. And if you have two elements, like say for example, you have hydrogen and carbon, and these two are have very similar electronegativity. So when these two atoms, carbon and hydrogen, are sharing a pair of electrons, they are shared equally. So there is no polarity created, no charges, opposite charges created, and therefore this results in a non-polar covalent bond. So the definitions, know the definitions of these. So polar covalent bond is something that is formed when the electrons are not shared equally, or they are shared unequally by two atoms that have different electronegativities. Is a bond that is shared by two atoms with similar electronegativities, or atoms of the same element, right? So let's say, for example, oxygen. A molecule of oxygen has two oxygen atoms. Now, even though oxygen is high in electronegativity, when it is paired with another oxygen with equal electronegativity, they end up sharing the electrons equally, and therefore it would be a non-polar covalent bond. Okay, so here in this example, you see how a molecule of water, now this is the red part of this atom is oxygen, and then you have two hydrogens attached to the same oxygen, and this makes a molecule of water. Now, as we talked about the electronegativity scale, we said oxygen is way at the top, and so it's a lot more electronegative compared to the hydrogens, and therefore see how the electrons, so the arrows indicate which way the electrons are displaced. They are displaced closer to oxygen, which results in a slight negative charge. So this little funny sign that you see here, this is kind of like, it indicates that it's a partial charge. Why is it partial? That's because these electrons that are displaced towards the more electronegative atom do not always stay there. They are kind of fluctuating between the two atoms, but they spend more time closer to the more electronegative atom. So that's why we call this as a partial charge, not a complete charge. Okay. And because the electrons, and every time the electrons move closer to oxygen, the oxygen will acquire this partial negative charge, and as a result of that, the hydrogen will end up with a partial positive charge. So we consider water as a polar molecule. The next kind of chemical bond is called an ionic bond. An ionic bond is a result of transfer of one or more electrons from one atom to the other atom, right? So you're literally like moving the electrons. It's not sharing, but actually transferring the electrons from one atom to the other. So what happens now? So far, let's say, for example, you have sodium, right? We talked about sodium, and we said it has, say, 11 as the atomic number, which means it has 11 protons, and it also starts off with 11 electrons. And protons and electrons have opposite charges, but since they are equal in number, they cancel out. And so the sodium atom does not have any charge. But to become stable, the sodium atom gives up its outermost electron, right? The valence electron that's given off. And what happens is it ends up with 10 electrons now. It started off with 11 electrons, but since it lost one of the electrons in order to become a stable atom, it has now 10 electrons only, whereas the proton number is still 11. So now there is a higher number of positive charges compared to the negative charges. And therefore, the sodium is no longer a neutral atom. It is now an ion with one positive charge. Okay? So it is a positively charged ion. We also call this as a cation. Now, if some other atom, such as say chlorine, takes up that electron given off by sodium, it will have one extra electron or one excess negative charge. And so the chlorine atom is no longer neutral. It now has a negative charge. And so we call this an anion. So because sodium and chlorine have opposite charges as a result of this transfer of electrons, they have mutual attraction, which keeps them together. So this attractive force between the positively charged sodium ion and the negatively charged chloride ion is called as the ionic bond. Okay. See, notice how the sodium is losing this electron and it is physically transferred. It's not like it's shuttling between the two atoms like sodium and chlorine atom, unlike what we saw in the water molecule, right? But the electron is actually transferred to the chlorine atom. And because of this, sodium ends up with a positive charge and the chlorine ends up with a negative charge, and the opposite charges attract, and therefore sodium and chloride ions stick together, and that force is called as the ionic bond. So all of these ionic substances are usually salts, and they have a specific structure, three-dimensional structure that keeps repeating, like it forms crystals, right? Like here, you have sodium chloride. Now, if you observe closely, the sodium chloride or table salt is in the form of crystals. And the crystal is a result of a specific arrangement of the opposite charge ions, the positive and the negative ions. Now, the last type of chemical bond we're going to be talking about is a weak chemical bond, also known as a hydrogen bond. Of course, there are several other weaker bonds, but we will not be discussing those. The only weak chemical bond that we'll be talking about is a hydrogen bond. But and the reason we talk about hydrogen bond is because it plays a very, very crucial role in the structure of water, and also is responsible for all the properties that water possesses. All the amazing properties water possesses is because of hydrogen bonds. So a hydrogen bond is formed when the hydrogen atom that is attached to an electronegative atom, such as oxygen, is also attracted to another electronegative atom, like another oxygen of a different molecule. So what happens here is basically the two water molecules combine, or they are joined through this hydrogen bond. Okay. Again, it's like an attractive force, but it is a weaker attractive force simply because it is a partial charge. So let's take a look at this example here. So I will go over that definition again. So a hydrogen bond is this dotted line. A hydrogen bond is formed between hydrogen that is attached to an electronegative atom and is also attached to another, or attracted to another electronegative atom of another molecule. So what we have here is ammonia. And when we discussed the scale of electronegativity, we said nitrogen is right behind oxygen. So nitrogen does have a pretty high electronegativity. So now why is this hydrogen attracted to this nitrogen? That's because nitrogen has a partial negative charge, hydrogen has a partial positive charge. And because these charges are partial, the bond is also weaker. Right? We use a dotted line rather than a solid line like we see in a covalent bond. Okay, so that's a hydrogen bond. Now this hydrogen bond can form between individual water molecules, okay, or between a water molecule and an ammonia molecule. Now what's common between the water molecule and the ammonia molecule is that they are both polar, right? So you will find hydrogen bonds forming between molecules that are polar. such as, say, water and ammonia. And this is the reason, the ability to form hydrogen bonds is the reason why ammonia, which is a liquid, is easily soluble in water, because it is able to form hydrogen bonds. Other weak interactions, like I was talking about, is van der Waals interactions. You really don't have to know these, but hydrogen bond is something that we'll be discussing throughout this course. And the last part is just a reminder that the shape always matches the function, right? Like, say, for example, the shape of a leaf, right, is flat and wide because the function of the leaf is to absorb light energy and perform photosynthesis. So a flat surface and a wide area will ensure a lot of light energy being absorbed. So the shape of various things that you see around is nothing but a reflection of its function, right? So as far as molecules are concerned, the shape of the molecule is determined by what orbitals it has. How many s orbitals, how many p orbitals, what is the combination, or when you combine all these s and the p orbitals, what is the shape that forms, and that determines the structure of a molecule. Like when you draw a water molecule, you would always draw like a V-shaped molecule. That's because of the orbitals that hydrogen and oxygen have and how they combine to form an in-between shape. So every molecule has a unique shape, and that shape is the key to its function. Okay. Now here you see an example of how now the natural endorphin, which is a pain reducer, that is naturally produced by our cells, and there is morphine right next to it, which is basically a synthetic pain reducer. Now, our body produces some amount of endorphin, which takes care of minor aches and pains, like say after a workout or a long workout session. You end up with aches and pains. Those can be handled by the endorphins that are produced by our body. But when someone has, like say, for example, surgery, right, any form of surgery, now the endorphins, now that creates a lot of pain, like excruciating pain. And the normal endorphin levels in our body are just not enough to calm down all the neurons that are screaming with pain, right? So you need something more, or you need to supplement these endorphins that are produced in your body with a synthetic substance called morphine. Now notice how morphine is a completely different molecule compared to the natural endorphin. But if you look closer, you will see that there is one certain specific region on morphine that matches the region on endorphin, and that is the key. So when scientists prepare synthetic molecules or medicines, they basically are trying to mimic the naturally existing one, like in this case, morphine. So the cells recognize this little part of morphine, and they are tricked into believing that it's actually an endorphin, and that's what calms down the neuron or the brain cell. The next part is, and this is the last part, I promise. This is basically, it's about how chemical reactions happen, what the structure of a chemical reaction would look like. So you will come across several chemical reactions, and they always have an arrow, which is either a double-headed arrow or an arrow that goes in one direction, like the one you see here. That just depends on what kind of a chemical reaction it is. Is it a reversible reaction or is it an irreversible reaction? Now, in this case, this is an irreversible reaction. And on the left side of the arrow, you have reactants that are going into the reaction. And then on the right side of the arrow, you have the products, right? So at the end of a chemical reaction, the reactants change into products. Now, for this to happen, see how the original bonds are broken and then there are new bonds that are created. So it's basically rearranging all the chemical bonds. That's what happens in a chemical reaction. Now, how does this happen? And we know how these chemical bonds are formed. They are formed because of the sharing or transferring of electrons. So it has to do everything with electrons and how they are arranged. Okay. Another example of a chemical reaction. This is the overall equation for photosynthesis. where 6 carbons are combined with 6 water. Now, why do we have to start with 6? Why can't we just say 1 carbon dioxide, 1 water? That's because whatever goes into the reaction must be accounted for. You cannot create matter from nothing, right? So here, when you make glucose that has 6 carbons and each carbon dioxide has 1 carbon, you have to start with 6 carbon dioxides in order to make a glucose with 6 carbons. Right? So this is called as balancing the chemical equation. Every atom in the reactants must be accounted for in the products, or vice versa. Right? Okay, so this completes this chapter, which is just the basics of chemical equations, how chemical bonds are formed, the two important chemical bonds, covalent bonds and ionic bonds, how they are formed, and then between the covalent bonds you have two types, polar and the non-polar, which depends on the relative electronegativities. And then of course you have finally the hydrogen bonds, which are formed between polar molecules. Okay, I'll see you again in the next chapter. Hello, so in this part of the chapter, we will be talking about the acids, bases, and pH. So we'll be defining what acids are and bases are and how we use the pH scale. Okay? So in water or in any aqueous solution, so an aqueous solution is something that uses water as the solvent. Okay, so in all of these solutions and in pure water, there is always an interaction between two water molecules in a way that one of the water molecules loses a hydrogen ion and the other water molecule picks up that hydrogen ion. So what you end up is a hydroxide ion and a hydronium ion, and sometimes we represent this as simply H positive. So when a molecule of water splits into two, you have one hydroxide ion or OH negative and a hydrogen ion or H positive. So water is in a state of dynamic equilibrium, which means the breaking of water molecules into hydrogen and hydroxide ions and then combining of those two and reforming water molecule happens at the same rate. So at any given point, the number of hydrogen ions are equal to the number of hydroxide ions. And they are both equal to 10 to the power negative 7 molars. So that is the concentration of hydrogen ions. So in the concentrations of hydrogen ions and hydroxide ions are equal in pure water. But when you add certain substances called the acids and the bases, these concentrations shift one way or the other. So there are either more of hydrogens, more of hydroxides, or you can also say, in other words, more of hydrogens and fewer of hydrogens, right? So how do we know how these concentrations are changing? We can convert these concentrations to something called as a pH scale. Okay, so we're going to be talking about the pH scale. So first of all, an acid and a base. So an acid is a substance that increases the hydrogen ion concentration, and the base is a substance that reduces the hydrogen ion concentration of a solution. Okay, that's the basic definition of acid and a base. So when we translate the hydrogen ion concentration on a pH scale, so this is what a pH scale looks like. It goes from 0 to 14, and you have 7 right in the middle. And so when you convert the hydrogen ion concentration to a pH value, you get one of these values in this range of 0 to 14. Any solution with a pH value of less than 7 is considered as acidic, and any solution that has a pH value greater than 7 is considered basic, and a pH value of exactly 7 or 7.0 is considered neutral. Okay, it's neither acidic nor basic. Another important thing you need to remember is how the pH changes as the hydrogen ion concentration changes. So you see this arrow that goes in this direction, and I have hydrogen ion concentration decrease. So anything that's inside the square brackets, That means you're talking about its concentration. So when I say, the way I would read this is hydrogen ion concentration. So the hydrogen ion concentration decreases as you increase the pH value from 0 to 14. Okay? So you have fewer and fewer hydrogen ions. Now that really doesn't make sense, right? Because your pH value is increasing, then why would your hydrogen ion concentration decrease? That's because your Okay, so basically what it means is pH value less than 7 is acidic, a pH value greater than 7 is basic, and a pH value equal to 7 is neutral. And also, as the hydrogen ion concentration increases, the pH value decreases, and the solution becomes more and more acidic. And as the hydrogen ion concentration decreases, the pH increases, and it becomes more and more basic. Okay, so there is the inverse relationship between the hydrogen ion concentration and the pH value. Okay, and that's why we saw that arrow in the previous slide go towards the opposite direction. Right? Okay, so now let's say I have water, just pure water, whose pH is 7, meaning my hydrogen ion concentration is 10 to the power -7 molars. Okay. And to this, I add a substance, okay, and the water that had a neutral pH until now has suddenly changed the pH value to 4. Now, how is that possible? What is going on in the background? So when you add some substance and the pH decreases, now earlier we said if the pH decreases, the hydrogen ion concentration increases, right? So now let's say my pH value is 4, which means my hydrogen ion concentration has changed from 10 to the power -7 to 10 to the power -4. Now, what does that mean? It means that my pH has, see how my original hydrogen ion concentration is 10 to the power of -7. My new hydrogen ion concentration is 10 to the power of -4, right? And we take the exponent of the hydrogen ion concentration and call that the pH. So my new pH value is 4. Now, if you compare the hydrogen ion concentration here and the hydrogen ion concentration that was originally in water, which is this, 10 to the power of -7, there is a change. Now, you would call this an increase, right? When it changes from 10 to the power of -7 to 10 to the power of -4, we call that an increase because of the negative exponent. Right? And every point in the exponent means times 10, right? Because it's 10 to the power a certain number, right? So a 3-point difference in the exponent from here to here is actually equal to 10 times 10 times 10, which is 8,000. So this is definitely an increase, and that increase is 1,000-fold. So now you have hydrogen ion concentration that is 8,000 times higher than pure water. And your pH has changed from 7 to 4. That means it has decreased, right? And your hydrogen ion concentration has increased. So that's what acids do. Acid is any substance that increases the hydrogen ion concentration. Okay? And that's what this substance just did. It increased the hydrogen ion concentration from 10 to the power -7 to 10 to the power -4, changing the pH from 7, which was neutral, to 4, which is now acidic. And now your water is acidic. And it has 1,000-fold more hydrogen ions. Okay, now let's say I take another fresh sample of pure water with a pH of 7, and now I add another substance to water, and now the hydrogen ion concentration has changed from 10 to the power -7 to 10 to the power -11. Okay, that means my pH value is now 11. And remember, any value of pH greater than 7 is considered basic, right? And also, we said as the pH value increases, the hydrogen ion concentration decreases. So here, your hydrogen ion concentration has decreased from 10 to the power -7 to 10 to the power of -11. So there is a 4-point difference, which means there is a 10,000-fold decrease in hydrogen ion concentration, and your solution or your water is now basic. Right? Okay, so I hope you understood the relationship between pH and hydrogen ion concentration. It is an inverse relationship. Okay, and also what these exponents mean. Exponents for hydrogen ion concentration mean the pH value, and a change in 1 point in the exponent is equivalent to 10 times hydrogen ion concentration, right? Okay. All right, let's also take a look at another concept, which is this in red. Okay. So at any point in any solution, when you multiply the concentration of hydrogen ions with the concentration of hydroxide ions, you always end up with, they always add up to 10 to the power 14. Okay, so you just, now what we do is, this is called the dissociation constant. So the product of the hydrogen ion and hydroxide ion concentrations is always equal to, or it adds up to 10 to the power 14. Okay, so let's take an example. If hydrogen ion concentration is equal to 10 to the power of negative 4, then your hydroxide ion concentration will be 10 to the power of negative 10. How did I get this number? I simply plugged in this number here, and I already know this constant, that's never going to change. So I just take the difference between the exponents here. 14 minus 4, that's negative 10 here. Okay, so my hydroxide ion concentration is 10 to the power of negative 10. And my pH value would be 4, because for pH, I need the hydrogen ion concentration. Okay, so the exponent of hydrogen ion concentration is the pH. So in this case, 4 would be the pH for this solution. Okay, let's take another example. If the hydroxide ion concentration is 10 to the power of negative 2, what is the pH of the solution? Now, it's a two-step process. First of all, I need to determine. Okay, let's take an example now. So I have my hydroxide ion concentration as 10 to the power of negative 2 molars. What is the pH of the solution? Now, to determine the pH of the solution, I need the hydrogen ion concentration, right? But all I know is the hydroxide ion concentration. So how do I use this number? I will plug in this number into that equation that you saw on the earlier slide, 10 to the power 14, right? So my hydrogen ion concentration would be 10 to the power negative 12, and therefore my pH would be 12. And with a pH of 12, the solution would be basic. Now, let's do another example. So these are some of the solutions I have with the corresponding pH values. So vinegar has a pH value of 2, milk pH of 6, soda pH of 5, hand soap pH of 10, water pH of 7. Okay, what is the hydrogen ion concentration of hand soap? Now, if the pH is 10, that means the hydrogen ion concentration is 10 to the power negative 10 molars, right? The hydroxide ion concentration of milk. Now, the pH of milk is 6, which means the hydrogen ion concentration of milk would be 10 to the power of negative 6, and therefore the hydroxide ion concentration of milk would be 10 to the power negative 8. What is the hydroxide ion concentration of water? Now, water has a pH of 7, therefore the hydrogen ion concentration is 10 to the power of negative 7. And when we subtract this from 10 to the power of negative 14, you have hydroxide ion concentration of water also as 10 to the power of negative 7. So they're both equal in pure water with a pH of 7. What solution has the most hydrogen ions? The one with the lowest pH. Here in this case, it would be vinegar. Which solutions are basic? Anything that is greater than 7 pH value would be basic. And in this case, it would just be the hand soap. There's one correction here. This is supposed to be a negative. OH negative. That's a mistake. Okay. Hi, so today in this chapter, or in this part of the chapter 3, we will be talking about molarity and making molar solutions. So this is another method or another unit for concentration. So you've already learned about one way to measure the concentration, which is milligrams per milliliter in the lab. So basically concentrations are measured as either volume over volume or mass over volume. But again, that may not be the most ideal way of measuring concentrations at all times. For example, say I'm making some hypothetical solution, which has, say, cotton balls, 1 kilogram of cotton balls and 1 kilogram of apples in a tub of water. Now, if I put those, I'm not going to have the same number or the density of those two substances in my tub of water, right? I'm going to have more of cotton balls because they have completely different masses. So a better way to calculate or to make solutions would be using moles, another kind of a unit. So in this, we go by numbers. How many molecules are there in a fixed amount of solution? Just like the concept of dozen. When you think of dozen, the number that comes to your mind is 12. So the same way, we have another such unit called as a mole. A mole is a certain fixed number of molecules of any substance. So if I say 1 mole of glucose, I'm referring to 6.02 into 10 to the power of 23 molecules. So that's a very big number, but it's a fixed number. The same thing if I say 1 mole of sodium chloride or salt, I'm still referring to 6.02 into 10 to the power of 23 molecules, which is the same number of molecules. It's only different types of molecules, right? So if I take, let's say, going back to that hypothetical solution, if I take 1 dozen of cotton balls and 1 dozen apples and then put them in water, they're each going to be the same number, right? I don't care about the mass at that point. I have the same number of these two items in water. The same way, molar solutions have a fixed number of molecules per volume of solution. Okay, so what exactly is this unit that we are talking about, which is similar to dozen? It's called the mole. Okay, it's called the mole. And just like a dozen is equal to 12 of anything, a mole is equal to 6.02 into 10 to the power of 23 molecules of any substance, right? So if I say 1 mole of glucose, I know I'm going to get this many molecules of glucose. If I say 1 mole of sodium chloride, I'm going to get this many molecules of sodium chloride. Okay, so that's what the moles are. Now, how do I use this to make molar solution? A molar solution is the number of moles of solute, that is the substance that you are making a solution of, per liter of solution. Now, solution is a combination of solute and solvent. That is, if I was making sodium chloride solution, the solute would be sodium chloride and the solution would be both water and sodium chloride combined, right? So that's what molarity is. How many moles, so how many of these you have in 1 liter of solution. So let's say if I have 1 mole or 1 molar solution, that means I have 1 mole of, let's say, sodium chloride in 1 liter of the solution, that is sodium chloride plus water. Okay. So if I say 2 moles of sodium chloride solution, that means I have twice this much in 1 liter. So the 1 liter is constant unless I say, okay, I want 1 mole and 2 liters of 1 mole solution. Then I change the volume. Otherwise, if the standard is 1 liter. Okay. So here, now, okay, so now we know what a mole is. Okay, now how do I count this many molecules? Now for a dozen, it's okay. I can count 12, not a problem at all. But this is an extremely large number. How do I count this many molecules? The easiest way is to first figure out the molecular mass of the substance or the solute that I'm trying to make a solution, right? So let's say I have sodium chloride. Okay, okay, so let's try and make 1 molar solution of sodium chloride. Okay, now the sodium chloride, so to figure out the mole, okay, or how much do I need to make 1 mole of sodium chloride, or to measure 1 mole of sodium chloride, is first we need to figure out the molecular mass, like I said earlier in the previous slide. So the molecular mass is basically the mass of all the atoms that are found in that molecule of that substance. So for sodium chloride, each molecule of sodium chloride has 1 sodium and 1 chlorine, right? And the masses of sodium and chlorine atoms are 23 and 35. So when we add these two numbers, we end up with 58 as the molecular mass of sodium chloride, right? And then, so that would be the molecular mass of sodium chloride, which means that is how much we need. So 58 grams of sodium chloride will be equal to 1 mole of sodium chloride. And when I say 1 mole, like the dozen, I mean 6.02 into 10 to the power of molecules of that substance. And here we're talking about sodium chloride. Okay, so quick review. Okay, so a mole of a substance. We need a mole of a substance. How do we measure that? We figure out the molecular mass of that substance by adding the atomic masses of all the individual atoms of that substance, and we get to take that many grams of that substance, and that would be equal to 1 mole, or also known as 6.02 into 10 to the power of 23 molecules of that substance. Okay, so now we know how much sodium chloride we need to weigh to make 1 molar solution of sodium chloride. Okay, so let's go ahead and make the solution of sodium chloride. Okay, so what I do is I just weighed out 58 grams of sodium chloride. Okay, so there's my 58 grams of sodium chloride. I'm going to put it in a graduated cylinder. And then I will add enough water to bring the final volume of that solution to 1 liter. It's not like you're going to add 1 liter of water. If you add 1 liter of water to this sodium chloride, it's going to exceed 1 liter, right? Because the sodium chloride powder that you added here also has some volume. And when you say 1 liter of solution, the solution is your solute, which is the sodium chloride, plus the solvent, which is water. So that makes up the solution. So we need 58 grams of sodium chloride in a total volume of 1 liter. So we just add enough water to bring that final volume to 1 liter and mix it, and then we have 1 molar sodium chloride solution. Okay? Now let's say I want to make 1 molar glucose. Now the molecular formula for glucose is C6H12O6. Now I have to first figure out the molecular mass of this molecule. Now the mass numbers of each of these atoms are given here, 12, 1, 16. So what do I do with these? Now remember, it's not simply adding these numbers, because each of these atoms appears several times in that molecule, right? So every molecule of glucose has 6 carbon atoms. So I'm going to say 12 times 6. So that would be the total mass of these 6 carbon atoms. And then I would take the mass of hydrogen, which is 1, and how many times it appears in the molecule, 12. So 1 times 12. And then I add the mass of all the 6 oxygens, and each oxygen has a mass of 16. So 6 times 16. And when I add all these 3 numbers, I end up with 180. So that's how much or how many grams of glucose I will weigh and call it 1 mole of glucose, which would have 6.02 into 10 to the power of 23 molecules of glucose. Now, again, I will do the same thing. I take a graduated cylinder, I put the glucose, 180 grams of glucose in there, and then add enough water to bring the final volume to 1 liter. Okay, so that's my 1M glucose solution. Now let's take a look at both these solutions we just made. We made 1M NaCl, we made 1M glucose. Now they are 2 different substances, but see how their concentrations are the same, 1M and 1M. Now what does that mean? It means that even though they are made of different solutes, like sodium chloride, this solution has sodium chloride as the solute, this solution has glucose as the solute. In spite of that, we have 6.02 into 10 to the power of 23 molecules of each of these substances dissolved in this 1 liter of solution. It's like having a dozen of cotton balls, a dozen apples in water, right? So we end up with the same number of molecules. It doesn't matter what substance you are making a solution from. Okay, so now we know how to make a molar solution, right? You take the molecular mass and you're going to weigh that many grams of that solute and then mix it with enough water to bring the final volume to 1 liter. Now, let's see. Now, most of the times I may not need 1 liter, or sometimes I may need more than a liter. And it's not like I'm going to need 1 molar solution all the time. I just need half a molar. So I should be able to make solutions of any volume and any molarity of any substance. So I should have that flexibility. So how do I go about that? So I have a general formula here that tells you how much of the solute you need. Okay, so that's what we start off with always, right? When we make a solution, we always start off by measuring the solute. Okay, so let's say I need 2 liters of half a mole of sodium chloride. How do I make that? First of all, I need to know how much of sodium chloride I need to measure out, right? So this is what I'm going to do. I'll take let's say I need 2 liters, okay? So I will just plug in these numbers in this formula. Volume, my final volume has to be 2 liters. So 2 times, my molarity is 0.5 or half. So I'm saying 2 times 0.5 and molecular mass of whatever substance you're making a solution of. So in this case, it's sodium chloride. And from our previous slides, we saw that sodium chloride has a mass of 58 grams, right? So 2 times 0.5 times 58, which is equal to 58 grams of sodium chloride. So I'm going to take 58 grams of sodium chloride, and this time I'm going to add enough water to bring the final volume to 2 liters, because my final volume that I need is 2 liters this time, not a liter, right? So this would be half a molar of substance, right? Because I'm taking this much of sodium chloride and then I'm mixing it in 2 liters of water. Okay. In this chapter, we will be talking about carbon and how important it is in building various molecules, and which eventually build the cells or the structures inside the cells. So carbon is considered as the backbone of various important molecules, biologically significant molecules such as carbohydrates, proteins, lipids, and nucleic acids such as DNA and RNA. And also in molecules such as ATP, which is considered the currency, the energy currency of a cell. So let's explore the various properties of carbon and why it is such a significant element in all living cells. So organic chemistry is a branch of chemistry that deals with carbon compounds. And not just carbon, but for a molecule to be considered as an organic molecule, there has to be carbon along with hydrogen at a minimum. And then in addition to carbon and hydrogen, it can have various other elements as part of these molecules. But the minimum requirement for an organic molecule is carbon along with hydrogen. So they can be very simple molecules, such as methane, which is 1 carbon and attached to 4 hydrogens, or to very, very complex molecules like the proteins or the DNA, which, for example, in the human DNA is about 2 meters long. So it's a very, very extensive and colossal molecule. So the organic molecules can range in not only the size, but also the versatility, how diverse these molecules are. And ultimately, the diversity of organic molecules comes down to the fact that carbon is highly diverse or versatile in how it forms bonds. Now, the only kind of bonds carbon can ever form is covalent bonds. Now, again, those covalent bonds could be polar or non-polar, depending on what the other atom is that is sharing, that is forming a bond with carbon, right? It comes down to their electronegativities. But whether it is polar or non-polar, carbon always forms covalent bonds. And it always forms 4 covalent bonds. And its usual the elements that usually form bonds with carbon are, of course, hydrogen, and then oxygen, nitrogen, sulfur, and phosphorus. So, like I mentioned before, carbon is very, very diverse. And this diversity comes from the fact that carbon has a very unique electron configuration. Which is basically the key to all of its chemical characteristics. So it can form 4 bonds, 4 covalent bonds, okay, because it has a valency of 4. Now, in chapter 2, we already discussed what valency is. Valency is how many electrons it needs, which is always equal to the number of covalent bonds it's going to form. So we can also call valency as bonding capacity. Now, carbon has a total of 6 electrons, with 2 electrons being placed in the first shell and the remaining 4 in the second shell, which is the valence electron shell for carbon. Now, the second electron shell has a capacity of 8 electrons, but carbon has 4 electrons, so it is half full, right? So it needs another 4, which means it has a valency of 4, which again means that it's going to form 4 covalent bonds. And these covalent bonds could be with multiple different atoms or the same atoms of the element, or it can form multiple bonds with the same atom, like a double bond, carbon with another carbon with a double bond, or carbon with another carbon, 3 bonds, or triple bond. But there's never a molecule where you would see carbon forming all 4 bonds with the same atom, or let's say, for example, another carbon. And that's because of the structure of the carbon atom. It has 1 bond that is away from the 3 other bonds. So there's a total of 4 covalent bonds formed, kind of like what you can see here. So this black dot circle here, that's the carbon. And you can see that there are 4 bonds radiating from the central carbon, right? Now, if you notice, these 3 bonds here at the bottom are facing in one direction, whereas the 4th bond is facing in the opposite direction. So that makes it impossible for a carbon to form all the 4 bonds with another atom, like the same atom. It's just impossible. But you can go up to 3 bonds, carbon forming 3 bonds with another atom, such as, say, another carbon or nitrogen, depending on the other atom's bonding capacity. So the number of unpaired electrons in the valence shell of an atom is equal to the valency, and it's also the number of covalent bonds it can form, right? So for the 4 most common elements in living cells, we have hydrogen with a valency of 1, and therefore the number of bonds it can form, or its bonding capacity, is also 1. Oxygen has 6 electrons in the outermost shell, which means it needs 2 more electrons to complete its valence shell, and therefore 2 is the bonding capacity. So the number of electrons an atom needs to complete its valence shell is equal to how many bonds it's going to form. So these are the 4 numbers you want to remember. This is something that you need to memorize: hydrogen 1, oxygen 2, nitrogen 3, and carbon 4. So the most frequent partners of carbon in forming these organic molecules are hydrogen, oxygen, and nitrogen. But sometimes you will see occasionally carbon bonding with maybe sulfur or phosphorus. Okay. So this is another example of a carbon compound, but just because it's a carbon compound, it doesn't mean that this is going to be organic, because there's no hydrogen. You just have carbon and oxygen. So this is a molecule of carbon dioxide, and you can see how each atom is forming the maximum possible covalent bonds. Like, for example, this carbon's bonding capacity is 4. So it forms 2 covalent bonds with each of the 2 oxygen atoms. And oxygen has a bonding capacity of 2, and you can see that each of these oxygens is forming 2 covalent bonds. So if I give you, let's say, a bunch of molecules with all of these covalent bonds, showing covalent bonds, based on your knowledge of the bonding capacity of these 4 elements, you should be able to determine whether the number of bonds is accurate, or if there's fewer or more bonds than what it's supposed to form. So that's incorrect bonding. Okay. So the carbon chains basically form the backbone of most of the organic molecules, and these chains can be in various forms. So you can have a chain of carbons that just goes linear, like you can see in this case, this one, this one, this one here. All of these are just like long chains of carbons. Now, this chain can further grow by, if like instead of the hydrogen, if you add a carbon. You can also do that. And this chain is only going to grow longer, kind of like your number line. There's no end. There's no end to how many carbons you can add to a chain of carbons. Okay? And another versatile nature of carbon is that it can form branched chains. So instead of one of these hydrogens, if we have a carbon, you can start another chain of carbons here. And same thing goes for every hydrogen. So in place of hydrogen, if you add a carbon, you can just extend that chain indefinitely. So that's a branched chain. So it can be profusely branched, which you will see in some of the organic molecules such as carbohydrates like starch and cellulose, glycogen. All of these carbohydrates have a highly branched chains of carbons. And another ability of carbon is to form double bonds. Like here you have, if you look at these two molecules, they look different because of how the covalent bonds are arranged. But you will also notice that there is a double bond between one of the carbons, like here, the first and the second carbon share a double bond. And here you have the second and the third sharing a double bond. Now, just the difference in the position of the double bond makes these two compounds entirely different. Right? They have different chemical properties, different physical properties possibly, but it all depends on where the carbon-carbon double bond is located. So that just creates more and more diverse molecules. And if you also count the number of carbons and hydrogens, these two molecules have the exact same number of carbons and hydrogens. But why are they two different compounds? That's because of how the covalent bonds are arranged or positioned. Okay? So that's the beauty of organic molecules, especially the carbon compounds. They can be very, very diverse. Now, carbon also has the ability to form closed rings. And we call these compounds as aromatic compounds. These are a specific group of organic molecules that have a signature aroma. So they form part of the aromatic compounds. But I mean, you don't have to memorize again any of these, but you should be able to, like, say, determine whether they share the same number of carbons, hydrogens. If they differ, how do they differ? What is the criteria? Like here, you have the same number of carbons that are located as or arranged as a straight chain. Here you have a branched chain. So in the previous slide, you saw how you have a bunch of organic molecules that are all made of carbon and hydrogen. So this group of organic molecules is called as hydrocarbons, simply because it is made of hydrogen and carbons, not carbohydrates. Carbohydrates are completely different. Carbohydrate means water, so carbon along with water. Here you have hydrocarbons, which is just hydrogen and carbon. Now, most of the fuels that we use, like propane, methane, butane, and all the fats, they all are made of hydrocarbons. And the reason we use them as fuels is because hydrocarbons have a lot of energy stored in them. So each bond in these hydrocarbons has a lot of energy, a lot of potential energy. So when you break those bonds, which is basically burning the fuel, all that energy is released, so they make excellent fuels. Like here, you can see a molecule of fat. And this is the most compact way to store a lot of energy in a living cell. So these long chains that you see here, these are completely made of carbons and hydrogens. So the backbone is made of carbon chains, and the carbons are attached to hydrogens, which are represented by these little white or gray circles. Now, moving on to the next concept here in carbon compounds or organic compounds. You have, now in the previous slide, again, with the hydrocarbons, we saw how two molecules that have the exact same number of carbons and hydrogens end up being different compounds, right? Because of the different arrangements of these atoms or bonds. So such molecules that have the same molecular formula but different arrangements are called as isomers, right, or different structures. And because they have different structures, they end up having different properties. We already discussed that in chapter 2, where the structure is so important for its function, or vice versa. Right? So because they have different structures, they would end up having different properties. So isomers are compounds that have the same molecular formula, but different structures, and therefore different properties. And you can have these arrangements. These different arrangements could result in either structural isomers, cis-trans, also known as geometric isomers, and enantiomers. Structural isomers would be just different covalent arrangements like the ones we saw earlier, where the carbon-carbon double bond was at a different position in each of these molecules. So that is nothing but a pair of structural isomers. Glucose and fructose are also an example of structural isomers. And then the next one is the cis-trans isomers, which are basically the difference in the arrangement of the covalent bonds around a carbon-carbon double bond. Let me show you an example here. Now, you can see here how, now the X's that you see here, these could be anything. They're like placeholders, right? So it could be an OH, it could be a group of atoms, or just one atom, whatever it is, but they could be anything. But notice how you have a carbon-carbon double bond. So that is the criteria. You have to have a carbon-carbon double bond to form geometric isomers or cis-trans isomers. And then you have different arrangements of the same two hydrogens and the two unknown groups, but you have them in different arrangements. Right? So on the first one, you have both of the hydrogens on the same side of the carbon-carbon double bond. And here you have the two hydrogens on the opposite side of the carbon-carbon double bond. Now, you know why the carbon-carbon double bond is important? That's because we are always referring to the carbon-carbon double bond to determine whether this is a cis arrangement or a trans arrangement. And then finally, enantiomers. Enantiomers are like mirror images of each other. So now you might think, okay, so why can't we just flip them over? It's highly impossible because a molecule is orientation is limited, or it is fixed. How it approaches a cell, how it is used by a cell, that orientation is fixed. Right? And the criteria for forming enantiomers is an asymmetric carbon, meaning a carbon that is attached to 4 different atoms or groups of atoms. It's not like where you have a carbon which is attached to 4 hydrogens. Even if there was a mirror image, you wouldn't be able to tell that it's a mirror image. Kind of like our hands, right? So each of these mirror images or enantiomers are different compounds. Okay? And the most common enantiomers would be most of the medications that we actually use, like ibuprofen. You will find ibuprofen in 2 forms, the 2 enantiomers. One of them is effective, that is, it is able to bind to the neurons and calm them down, because the neurons are the ones that are affected, or they give the sensation of pain, right? So all the pain relievers, they attach to the neurons and then they calm the neuron down. So only one of these 2 enantiomers is able to calm or alleviate the pain, okay? Whereas the other one is ineffective because it is flipped. Okay? And the same thing goes for albuterol, which is a bronchodilator, or it improves the movement of air in the airway, okay, or to the lungs. So this is a medication that is used to relieve the symptoms of asthma. And again, they come as enantiomers, and only one of them is the effective form. The other one is a mirror image and ineffective. Okay, moving on to the last part of this chapter, which is chemical groups, also known as functional groups. And we call these functional groups because they determine the function and the properties of a molecule, an organic molecule. So these are groups that are attached to the carbon skeleton. Like here, for example, you have estradiol or estrogen and testosterone. Now, when you look at them, they are kind of similar, yet they create such a great distinction in humans, right? In mammals, whether it's going to be a male or a female, develop male characteristics or female characteristics. That's the impact of these functional groups. So the basic skeleton of each of these molecules is almost identical, right? And the difference is the type of groups that are attached to these carbon rings. Remember, we said carbon chains can also form rings. So these are nothing but carbon rings. And you have different groups attached. And that's what makes them completely different molecules, which have drastically different effects. So there are several such functional groups. And each of these functional groups gives certain properties to the entire molecule. So they determine the function of that entire molecule. And these are the functional groups that you have to memorize. You have to know their structure, what they look like, what each group is made of. Like, say, for example, hydroxyl group. You should know what it looks like. What are the 2 or 3 atoms that make up a hydroxyl group, and so on, right? And what are the properties? If there is a hydroxyl group attached to a molecule, what would happen to the properties of that molecule? So all that information about each of these functional groups. So you have this table here. The very first one is, okay, so the very first one is the hydroxyl group. And a hydroxyl group always has 1 oxygen and 1 hydrogen. Now in chapter 3, we saw, and also chapter 2, we saw how the electronegativities, the difference in electronegativities of atoms makes a covalent bond either polar or non-polar. And in chapter 3, we also saw how the molecules that are polar or ionic are completely soluble in water, right? So here, knowing that oxygen and hydrogen have different electronegativities, we can for sure say that the bond that is shared by O and H is going to be polar. So when you add such a polar group to any molecule, it is going to make that compound or that molecule hydrophilic, because all polar substances dissolve in water, right? So here, for example, the compounds that usually have the OH as the functional group are called as alcohols. An example of this would be ethanol, right? And then carbonyl group. Carbonyl group is made of a carbon that has a double bond with oxygen. And the compounds that have this carbonyl group are usually ketones and aldehydes. Okay. And again, because of the difference in electronegativities, the carbon oxygen share polar covalent bonds. So any molecule that has carbonyl group as the functional group is also going to be hydrophilic or soluble in water. Now, why do we have 2 different compounds that could have this carbonyl group? Now, the difference in these compounds is based on the position of the carbonyl group. In one group called the aldehydes, you will see that the C double bond O is somewhere within the chain of carbons, right? Whereas in ketones, you would find the C double bond O on the terminal carbon, either the first or the last. Okay, so that's the difference. The position of the carbon double bond O or the carbonyl group determines whether it's going to be an aldehyde or a ketone. And then the next one is carboxyl group. Now here, carboxyl group is made of a carbon that is attached to an oxygen with a double bond. And the same carbon is also attached to an OH or a hydroxyl group. Right? So when I give you, say, some structures and ask you to pick the molecules that have a carboxyl group, carbonyl group, you cannot count the carbonyl group, the C double bond O, as one of them, because C double bond O is not by itself, but it is part of a larger group, which is a carboxyl group, right? Same thing goes for OH. I cannot just separate this and say, okay, this is a compound that has an OH, so this is an alcohol. I cannot do that because the OH is part of a larger group called the carboxyl group, right? Now, the carboxyl group, COOH, is usually part of all the organic acids. Now, why do we call this an acid? Now, by definition, in third chapter, we already talked about acids and bases. By definition, any compound that releases hydrogen ions is an acid. right? So here, if you notice here, from the OH, the O loses the hydrogen. So basically, this group is releasing hydrogen ions, which by definition makes it an acidic group. So carboxyl group is an acidic group. Okay. Then the next one is the amino group, or N, that is attached to 2 hydrogens. Okay. And this amino group is normally found in amino acids. Amino acids are the building blocks for all the proteins. Okay. So the amino group, again, by definition, is a basic group. Why is this a basic group? Because like we studied in chapter 3, a base is a substance that accepts hydrogen ions or picks up hydrogen ions, right? So here, if you notice, the amino group adds on a hydrogen ion, turning it into an ionized form of amino group, which is NH3 positive. So that makes it a basic group. Okay? So the carboxyl group is acidic, amino group is basic. Then the next one is sulfhydryl group. The sulfhydryl group is made of sulfur and hydrogen. And again, sulfur is, or it belongs to the same group as oxygen. So the SH group is very similar in function and properties to the OH group. And the compounds that contain SH are called as thiols. And again, this is going to be a polar compound. And then you have the phosphate group. The phosphate group is very, very important. We will be running into this group several times throughout this course because it is a very important functional group of the energy currency molecule, which is the ATP. So the P stands for phosphate. So you have, and the T is the triphosphate. So you basically have 3 of these groups, these phosphate groups, attached to adenine, which makes one molecule of ATP, or the energy currency. And also DNA has a phosphate group as well. And then the final group that we're going to be talking about is a methyl group. Methyl group is carbon attached to 3 hydrogens. Now by itself, now definitely when you look at something like this, a carbon and hydrogen, they have the same electronegativities, so they form non-polar covalent bond, which makes them non-polar or hydrophobic. So all non-polar substances are hydrophobic. So as a CH3 group, it is hydrophobic. But of course, you can have other groups also attached to the same molecule. Like here, you can see that there is an amino group, right? There is a carbonyl group, and then there is the methyl group. So these could just be one of the several functional groups added to the same molecule, or it could be the only functional group, in which case the molecule would be hydrophobic. Now, how is this significant? How is this methyl group significant? It plays a very important role in cell differentiation. Okay? We all start our life as a single cell. And look at us now. We have so many different types of cells, not just many cells, but different types of cells like blood cells, skin cells, muscle cells, neurons, right? So you have enormous number of bone cells, right? All of these are different types of cells that all originated from one single cell. And that's because of the difference that is caused by different genes expressed. So when we start off, we have 100% of genes in a cell, right? And that cell divides into 2. So now we are 2-celled embryo, and then those 2 cells divide again, making 4-celled embryo, and so on. Now, after a certain stage of embryonic development, methyl groups are strategically laid on the DNA, or they are added to the DNA. Once a methyl group is added to DNA or a gene, it is turned off permanently. So what happens is you have a different methylation pattern laid out in different groups of cells, which eventually develop into different types of cells. So yes, you have 100% of the genes in every single cell in your body, but not all genes are expressed in every cell, right? In every tissue. So when genes are expressed, proteins are made, and proteins determine the nature of the cell, the structure of the cell, right? So the methylation pattern results in different sets of genes expressed in different cells, leading to cell differentiation. So here we will be talking about the ATP, like we said, the energy currency of the cell. So ATP, or adenosine triphosphate, is basically a molecule that looks like this. It has 3 phosphate groups. Okay, and you also notice a lot of negative charges here on phosphate. That's the characteristic of phosphate group. It always has a negative charge, which makes ATP always negatively charged. Also DNA, because it has phosphate group, also is always negatively charged, right? So there are 3 of these phosphate groups attached to an adenosine, which is one of the building blocks of ATP, of DNA and RNA, like ATGC. That's the A we are talking about here. So this molecule, in some aspects, it is kind of similar to your nucleic acids, such as DNA and RNA. Now, why is this particular molecule used as the energy currency? That's because these 3 phosphate groups have a lot of energy stored in them. Now, how do they have so much energy? That's because now notice how there are so many negative charges. We start off with, let's say, adenosine and 1-phosphate. So adenosine monophosphate has a negative charge. You're adding the 2nd phosphate, which also has a negative charge. You're trying to add a negative to a negative, and only opposite charges attract each other. But here you're trying to put together like charges, which takes a lot of energy. And that energy comes from our food. And that process is called as cellular respiration. We'll be talking about that in chapter 9. But just so you know why ATP has so much energy, this is the reason. When you're adding several like charges, you need to invest a lot of energy to combine all these negative charges. And then imagine when you're trying to add the 3rd phosphate to these 2 phosphates. You need a lot more energy. So ultimately, now the energy cannot be destroyed. All the energy that goes into building ATP can be ultimately used to do all the cellular functions that our cells do, or any living cells do. So when you break one of these bonds, like here, the 3rd phosphate is removed, and you're left with adenosine diphosphate, or ADP, and then the phosphate is released. And when the bond is broken, see how much energy is released. Now, when you break this bond, still more energy is going to be released. So that's the purpose of building these ATP. So you have this currency. You're investing your energy, which comes in the form of food, into these ATPs. And then when your cells need energy to do all the different functions that they do, they use this energy currency. And when they break them, they release energy. All right, so in this chapter, we talked about the versatility of carbon, all the different forms of isomers, and the functional groups, and also the importance of ATP. In the next chapter, we will be talking about the biologically significant molecules, also known as macromolecules. See you there. In this chapter, we'll be talking about the 4 major molecules that are found or that make up a living cell. And these are also called as macromolecules because they are very large molecules with sometimes even hundreds or thousands of atoms combined together into one molecule. And they make up most of the solid mass of any living cell. So here we'll be talking about carbohydrates, which is one of the groups of macromolecules. And you're familiar with carbohydrates. There's sugars, starch, cellulose. All of these are, they belong to the carbohydrate group. And then you have proteins, which are the most important molecules because they perform pretty much every function that a cell performs. So these are kind of like the tools of a cell. And you have nucleic acids such as DNA and RNA. These are also macromolecules. They are very, very large molecules made of thousands of atoms put together. And then the last group is the lipids. Lipids are, they perform various functions and they have a diverse structure. You have very diverse molecules grouped in these lipids. The common feature of the lipids, all the diverse molecules that make up the group lipids, is that they are all hydrophobic. So any macromolecule that is hydrophobic is labeled as a lipid. Okay? Examples of lipids would be fats, phospholipids, which are the molecules that make up any membrane in a cell, whether it is the plasma membrane, whether it is the nuclear membrane, or any other membranes found in a cell. They are all made of primarily phospholipids. And of course, there are other components, but the main ingredient of any membrane, biological membrane, is phospholipid. And then you also have cholesterol, which is primarily found in the animals. So these are all the lipids. So we'll now, out of these four groups, the only groups that form these chains of molecules, you see how this looks like a chain? This is called as a polymer. Poly is many. Polymer is many molecules or many structures joined together into a chain. And each of these, like if you look at this looks like a string of pearls, right? And each pearl or the circle you see here is called a monomer. Now the monomers are basically the building blocks of all these molecules, and each group has a different type of monomer, and the monomers put together form a polymer. So we will be talking about what specific monomers are found in each of these polymers. Now, among the four groups, that is the carbohydrates, proteins, nucleic acids, and lipids, lipids do not form polymers. So they do not form repeated units put together like this chain or a polymer. So that is one unique trait of lipids, that they do not ever form polymers. Whereas carbohydrates do form polymers. There are some that do not form polymers, but there are polymers, very well-known polymers in the carbohydrates. Proteins, every protein is a polymer. And then nucleic acids such as DNA, RNA, every RNA is a polymer. So only the carbohydrates, proteins, and nucleic acids form polymers, that is repeating units joined together. Lipids do not. And another unique quality of lipids is that they are all hydrophobic. So, like I discussed earlier, polymer is a long chain that consists of many building blocks, and these building blocks are called as monomers. So out of the four polymers, out of the four macromolecules, only carbohydrates, proteins, and nucleic acids form polymers. So how are these polymers formed? They are formed when monomers are joined together, right? So it all starts with two monomers coming together, right? And then that forms a chain of two monomers. And then you add a third monomer. It becomes, the chain grows into 3, and then 4, and then 5. So a monomer is added in each of these reactions. So all these are nothing but chemical reactions. Okay? So adding one monomer at a time. This reaction results in the removal of a molecule of water every time a monomer is added to the chain. Right? And because water is removed, this reaction is also called as dehydration reaction or dehydration synthesis. Okay? So two chemical reactions are extremely important for polymers as far as polymers are concerned. Polymers are built by dehydration synthesis or dehydration reaction, where as each monomer is added to the chain, you have a molecule of water removed, right? And then the opposite of this is when you have a polymer and then you're trying to break it down into individual monomers. Okay? So that process or that reaction is called as hydrolysis. Hydro is water, lysis is to break. So this reaction where the monomers are separated or the polymers are broken down requires addition of water. So for every monomer separated, a molecule of water is added. Remember how we removed the water when we added the monomers to form a polymer. And then now, when you're removing the monomers while breaking down the polymers, you add the molecule of water back. Right? So how exactly are these monomers joined? Okay? So these are the two reactions. Again, just to recap, we have dehydration reaction that joins the monomers to form a polymer, and then a polymer is broken down or disassembled into individual monomers by hydrolysis. So just remember the word lysis, which means to break. So that would be the reaction that breaks down the polymers. So here in this illustration, you can see how you have a short polymer made of 3 monomers. And then notice how it has a hydrogen. So this incoming monomer also has a hydrogen here, right? So this hydrogen and then the monomer that is being brought or being added to this chain has an OH. So when these two combine, they are removed as a molecule of water. And the result of that is that a bond is formed. Now we said a solid line is a covalent bond. So there is a covalent bond that is added between 3 and 4 now. So now the polymer is slightly longer than before, right? So now it has 4 polymers. Then you can just keep going depending on what type of molecule the cells are building. Right? Now, when would you see something like this? An example of this process. Like say, for example, you have photosynthesis. Photosynthesis is when glucose is made, right? So if you consider glucose as individual monomers, now all of that glucose that is made during photosynthesis is converted to starch. Now starch is nothing but a long chain of glucoses. So when you combine the individual glucoses to form a starch molecule, that is nothing but dehydration reaction. So this happens in the plants right after photosynthesis. Okay? And then hydrolysis. Where exactly does hydrolysis happen? Your body, like say, for example, digestion, right? When we consume food, all the food we consume, whether it is a plant source or animal source food, they are all made of polymers, such as starch. Then you have DNA, RNA, lipids. Of course, lipids are not polymers, but you have all these macromolecules. And of course, proteins, which are polymers. So when you consume food, it first gets digested. So what exactly happens during digestion? Now, the food we consume is a polymer, which is a very large molecule. So our cells will have a hard time absorbing or taking up those extremely large molecules. So the digestive system breaks down the food or the polymers into individual monomers so that they are now easily absorbed into the bloodstream. So that's what our digestive system does. It breaks down the polymers into individual monomers by a process called hydrolysis. Okay? So for every bond that is broken, like say, for example, here is a short polymer that we are breaking down by hydrolysis. So a molecule of water is added and this bond between 3 and 4 is broken. Then when you want to break the next bond between 2 and 3, another molecule of water has to be added. And then yet another molecule of water has to be added to break down the bond between 1 and 2. Right? So this is an interesting fact here also, where you see a chain of 4 monomers. In order to break it down completely, you need 3 water molecules. Right? And here, so basically what you want to remember is that for every bond made, a molecule of water is removed. For every bond broken, a molecule of water is added. So if I have, say, a polymer that is 100 monomers long, I would just need 99 water molecules to break it down completely into 100 monomers. Right? So one less than the number of monomers. So these two are very, very important chemical reactions as far as polymers are concerned.
Most biological molecules are very large and are built by assembling small molecules, or monomers, into long chains. The resulting molecules are called macromolecules, or polymers. A process of linking monomers, called dehydration synthesis, involves the removal of 2 hydrogen atoms and 1 oxygen atom to form water. One way this might happen is diagrammed here. where several generic monomers are shown with OH groups that could be used for linking. The animation illustrates the joining together of monomers by dehydration synthesis, catalyzed by a polymerase enzyme, and the reverse process, in which added water results in hydrolysis, catalyzed by a hydrolase enzyme.
Okay, so all living cells have all of these 4 macromolecules, but each species, each cell type has a different ratio. And also, the number and the type of macromolecules is species specific. So every species has a different type and a different ratio of these macromolecules. So the first group of macromolecules we are going to be talking about are the carbohydrates. So the main purpose of carbohydrates is that they are excellent fuels. They have a lot of energy stored in them. Like say, for example, starch or sugars. They all have a lot of energy, right? Which when broken down can be used to make ATP, which is the energy currency, which is then used to perform all the cellular functions. Okay. So there are several carbohydrates, and carbohydrates can exist as monomers, dimers, polymers. So they can be different sizes of carbohydrates. The simplest carbohydrates are called as monosaccharides. Now here's a new word, saccharide, which literally means sugar, right? So monosaccharide is a single sugar molecule. Disaccharide is a double sugar molecule. And polysaccharide is more than 2 sugar molecules combined into one molecule, one giant molecule. Like say starch or cellulose. All of these are extremely large molecules that are made of several monosaccharides. Okay? So the monomers for carbohydrates are also known as monosaccharides. Okay? So for every polymer group or every macromolecule group, there is a different type of building block or different type of monomers. For the carbohydrates, it is the monosaccharides. Okay. So usually monosaccharides have a formula that is multiples of CH2O. They all have this ratio of carbons, hydrogens, and oxygen. Like say, for example, here you have glucose, and this is also the formula for fructose and galactose, which are 3 most important monosaccharides. So for glucose, you have C6H12O6, which is basically the same ratio as what you see here. So glucose is the most common monosaccharide. That's because it is the building block for most of the other carbohydrates. Okay? And you can classify the monosaccharides based on different criteria. One is the location of carbonyl group. So basically C double bond O is the carbonyl group that is present in all of the monosaccharides. And again, based on the position of the carbonyl group in the monosaccharide, you can either call it an aldose or a ketose. You heard these words, similar words, that is aldehyde and ketone. But here we are just modifying that slightly because we're talking about sugars, and all sugar names end with OSE, like glucose, fructose, galactose. So here, the carbonyl group location makes it either an aldose or a ketose. And then the other criteria is the number of carbons. So the smallest one would be a 3-carbon sugar. You call it a triose. So here you see how you have trioses. So 1, 2, 3 carbons, 1, 2, 3 carbons. These are both trioses or 3-carbon sugar. Then you have pentoses. That is 1, 2, 3, 4, 5, and so on. So 5 carbons each. So these are pentoses. And ribose is the sugar component found in DNA and RNAs. Of course, in DNA, it's a slightly modified. We call it as a deoxyribose. But the sugar found in RNA is ribose. So that's where we'll come back to this sugar when we get to the nucleic acids, that is the DNA and RNA. And then you have the hexoses, which are 6-carbon sugars, and these are the most common sugars. So when we say sugar, this is what we usually refer to. So there is glucose, galactose, and fructose. So know the list of monosaccharides. So these are the 3 most common monosaccharides, and among these, glucose would be the most common monosaccharide. Also, based on the position of the carbonyl group, C double bond O. Now we said if it's on a terminal carbon, it is an aldehyde. In this case, we call it an aldose because we're talking about sugars. And then if it is somewhere in the middle of the chain, the carbon chain, then it would be a ketone, or in this case, ketose. Now, monosaccharides are very important fuels. They are used, especially glucose and fructose, are used during cellular respiration. So cellular respiration is the most important process where ATP is made. And for this, usually the cells use glucose or sometimes fructose. So they serve as a very important fuel for the cells. And these are just different forms of sugars, that is the hexoses or the 6-carbon sugar. So this would be, because there is a C double bond O at the end, this would be an aldose, right? So in the solution form, so when sugars, like say this is the powder form of glucose, but when you mix it in water, this is what happens to glucose. It closes up into a ring structure, okay? A 6-carbon, so an hexagonal structure. Now moving on to the next category of carbohydrates. So we talked about monosaccharides. Here we are going to be talking about the second group called as the disaccharides. Di is 2, saccharide is sugar. So 2 monosaccharides are joined to form a disaccharide. Okay. And how are they joined? They are joined by a line. A line represents a covalent bond, right? And of course, this is through dehydration reaction, where a molecule of water is removed and the 2 monosaccharides are joined by a covalent bond. The covalent bond in each group has a specific name. So here, the name of the covalent bond found in carbohydrates in general is called a glycosidic linkage. Okay, so it's just the name given to the covalent bond that you would find between individual monosaccharides. Like here, for example, you have a molecule of maltose. Maltose is one of the 3 most important and commonly found disaccharides. The others are sucrose, and the last one is lactose. Right? So to make a molecule of maltose, you need 2 molecules of glucose combined through a dehydration reaction, and they are joined by a glycosidic linkage. Right? And to make a molecule of sucrose, which is basically table sugar, you would need a molecule of glucose combined with a molecule of fructose through dehydration reaction, and a glycosidic linkage is formed between them. Now, if you just keep adding more and more glucoses, you would end up removing more and more water molecules and also extending this chain. Polysaccharides are multiple. Poly is multiple saccharide sugar. So there are more than 2 monosaccharides joined. It's called a polysaccharide. There are several important functions that the polysaccharides perform. Some of them perform energy storage. They're called as storage polysaccharides. And there are others or other polysaccharides that perform structural function, like cellulose, chitin. All of these are structural polysaccharides. So you have basically 2 types of polysaccharides, storage and structural. Starch is a storage polysaccharide, and it is made of a whole lot of glucose molecules joined together by glycosidic linkages. And this is a storage polysaccharide found in plants. Animals do not make. They can definitely use starch, which is always plant-based. So starch is made only by the plants, and it is used as fuel by the plants and also by animals when they consume it. And then glycogen is another storage polysaccharide found in animals. Like we have all the excess glucose from the blood or from the food that we consume. Eventually this glucose goes into the blood, and if there is too much glucose in the blood, the insulin secreted by the pancreas triggers or stimulates the liver cells and the muscle cells to pick up this excess glucose molecules, join them together by dehydration synthesis to form glycogen and store it for later use. Okay. So this is the structure of starch and glycogen. They are both made of glucoses. Right? So hundreds of glucose molecules join together to form either starch or glycogen. And starch is a plant storage polysaccharide. Glycogen is the animal storage polysaccharide. Now, moving on to the next type of polysaccharides, that is the structural polysaccharides. There's cellulose, which is the main component of the plant cell wall. The cell wall performs a very important structural role in a plant cell. It maintains the shape of the cell. It also is subject to a lot of pressure from inside and outside the cell. So there has to be some sort of a material that can withstand all this wear and tear. And cellulose is the perfect molecule. It is a very tough molecule that can withstand all of this pressure. So again, the cellulose is also made of glucose, but it is made slightly from a different glucose called the beta glucose. So glucose exists in two different forms, the alpha and the beta. So cellulose involves the beta glucose. And the reason why cellulose is so tough is because you notice how there are these parallel strings of glucose molecules. And then there's also, so there are these lines, that is the covalent bonds, also known as the glycosidic linkages, that hold these individual chains together. In addition to that, you also have these dotted lines here, right? Those are the hydrogen bonds. So this looks almost like a fabric. If you look under the electron microscope, which is a very, very powerful microscope with a lot of resolution, you will notice that the cellulose fibrils actually look like a fabric. So this makes cellulose the perfect molecule to form the cell wall. And the reason cellulose makes these hydrogen bonds with the parallel molecules or chains of glucose molecules is because of the orientation of the OH groups. Now here in starch, you see how all the alpha glucoses have the OH on the same side. Right? Here you have beta glucose. So it's basically just flipped over, right? So it's kind of like a cis and trans arrangement, something that we learned in chapter 4, right? So, I mean, that's how this course is designed. Anything you learn in the previous chapters is actually applied in the later chapters. So it's very important for you to remember all the material that is that appears in the earlier chapters. So this is the cis and the trans arrangement. So this arrangement allows the OH to form a hydrogen bond with the other chain of the parallel chain. So those hydrogen bonds are possible because of this trans arrangement of OH groups. So this is the beta glucose. Now, how is this different? It's different because when we consume plant source food, right, like say a salad, okay, it will have starch. It will also have cellulose because the salad is made of leaves. Leaves have cells and cells have cell wall that is made of cellulose. And inside those cells, you will also have starch, right? So starch can be broken down by our digestive system, no problem at all. So we can easily digest starch and get a lot of energy from the starch. But the cellulose, again, there is a lot of glucose molecules in the cellulose also, but we unfortunately cannot use all of those glucoses. That's because our digestive system does not have the enzyme that can break down the beta glycosidic linkages that are found in the cellulose. So this cellulose forms the insoluble fiber, right? When you look at the nutrition labels of some products, you will see that there is insoluble fiber listed there. So that's nothing but cellulose. So, now, is it a waste, complete waste? Not really. The cellulose actually works like a pipe cleaner, if you will. So it basically cleans the inside of our digestive tract. So that's the reason fiber is such an important part of the diet to maintain a healthy digestive tract. Okay. But there are some animals that can actually digest cellulose also. That's because they have certain microbes in their digestive tract that can produce the beta, the enzyme that breaks down the beta linkages. And therefore, like say, for example, all the cattle, the cows, the sheep, they feed on mostly plant material, right? All of their food is nothing but plant material. They're all herbivores. So they have to make the most of whatever they are consuming, right? So they have these microbes or a specific type of bacteria that actually produce enzymes that can hydrolyze or digest cellulose. Same thing goes for termites. The termites also have some of these microbes in their gut, and that's the reason the termites are able to eat through the wood. Wood is nothing but, again, it's all plant material, and it does have cell walls, a lot of cellulose. So the termites make use of the glucose that is part of the cellulose molecules with the help of these microbes digesting the cellulose for them. The other structural polysaccharide besides cellulose is chitin. Chitin is unique carbohydrate. This is the only carbohydrate that has all the 4 biologically important elements like carbon, hydrogen, oxygen, nitrogen. All the other carbohydrates have only carbon, hydrogen, oxygen. Chitin also has nitrogen. Now, where is this found? This is also a structural polysaccharide, meaning it is very sturdy. So it can be used as the exoskeleton of the insects. Now, if you look at beetles, there is a hard coat on them. Now, that is made of chitin. Another place where you would find chitin is the cell walls of fungi, such as mushroom, yeast, morels. All of these are fungi, and they all have cell walls just like plants, but the cell walls of fungi is made of chitin, another structural polysaccharide. So notice how this has a nitrogen. This is the only carbohydrate that has a nitrogen. So the next category of macromolecules are the lipids. And like I said earlier, the lipids are a very diverse group of molecules, but the only common thing that they have, that they all share, is that they are mostly hydrophobic. There are some that are slightly hydrophobic. We'll talk about them in just a minute, but that is kind of like a rule in the lipids. All organic molecules, macromolecules that are hydrophobic are considered to be lipids. And lipids also do not form true polymers, like they do not have multiple monomers joined together or similar pieces joined together, kind of like, a string of pearls. We do not see that in the lipids, but they play very, very important roles. For example, the phospholipids, they form any kind of membrane in the cell. Any living cell. You take any living cell, the plasma membrane, nuclear membrane, endoplasmic reticulum, the membrane around all the organelles, they all are made of phospholipids, which is one of the category of lipids we will be talking about. The other two are fats and steroids. So the fats, they are made up typically, this is the first category of lipids we are going to be discussing, and fats are made of 2 components. One is the glycerol, the other one is fatty acids. And the glycerol has 3 hydroxyl groups, and each of these takes on a fatty acid chain. The fatty acid chain has mostly carbons and hydrogens, giving it a lot of non-polar covalent bonds. So a molecule of fat has a glycerol with 3 molecules of fatty acid attached to it. So it's also known as a triglyceride. And the fatty acids, they are basically of 2 types. One of them is saturated, and the other one is unsaturated. So when we talk about saturated or unsaturated fats, we are talking about how many hydrogens do the carbon chains have. Do they have the maximum possible hydrogens, like the ones that you see here? So here you see a chain of carbons attached to the maximum possible hydrogens, right? So each carbon forms 4 bonds. 2 of those bonds would be with the neighboring carbons, and the remaining 2 would have hydrogens. So that's the maximum of hydrogens they can take up, except the last one, which can be attached to 3 hydrogen atoms. So if you have all three chains, now the three chains need not be identical, they can be of different types, but as long as they all have the maximum possible hydrogens, they are considered as a saturated fatty acid or saturated fat. And the other one is unsaturated fat. Unsaturated fats usually have one or more missing hydrogens. So the unsaturated fats are unsaturated in terms of hydrogens. They have fewer hydrogens compared to saturated fatty acid. So let's say a couple of these hydrogens are missing, right? Then what would happen to these two bonds? What happens is the carbon then binds to the other carbon, the neighboring carbon, with a double bond. So it compensates for the lack of enough hydrogens by forming double bonds. So by definition, a saturated fatty acid has a maximum possible hydrogen atoms, and it does not have any carbon-carbon double bonds. Whereas unsaturated fatty acids, because they have fewer hydrogen atoms, the carbon-carbon that do not have all the hydrogens they need, they eventually form double bonds with each other. So saturated fatty acids usually have carbon-carbon double bonds. So what impact does that have? Like if you notice here, these two chains of this fatty acid molecule are straight, which means they are all single bonds, carbon-carbon single bonds. Of course, you don't see the carbons and hydrogens. Just for simplicity, it's represented like this. So each of these lines indicates covalent bonds with between carbons. But when you come to the third chain here, this one has a double bond. Now that indicates that there are two hydrogens missing, one on each of these neighboring carbons. So how do they compensate for that? They just form a double bond with each other. And this double bond creates a bend or a kink in the fatty acid molecule. Okay? And so when you have molecules like this that are kinky, they have these kinks, it's impossible or it's really hard to pack them tightly, like close together, which is a good thing for fats because that way they do not stick together and they remain liquid at room temperature, such as olive oil or sunflower oil, corn oil. Right? So majority of the plant oil, fats or plant oils are unsaturated fatty acids. Now, on the other hand, if you have saturated fatty acid chains like the ones you see here, no double bond at all. Therefore, all these three chains are going to be straight chains, which means it is possible to pack such molecules closely, okay, into a compact structure, which is seen in the solid state. So all saturated fatty acids have a solid state at room temperature, like butter, lard, coconut oil. They all have saturated fatty acids. So that's the basic difference. The only exception of the animal fats being saturated would be the fish oils. Fish oils are considered healthy because they are unsaturated, just like plant fats, which makes them a healthy choice. And out of the vegetable or the plant source oils, mostly they are unsaturated, but there are a few exceptions like coconut oil. They have, the coconut oil has unsaturated fatty acid, which explains why coconut oil is solid at room temperature. Another kind of process that kind of converts or gives unsaturated fatty acid the texture of saturated fatty acid would be hydrogenation, which is basically adding the missing hydrogens back. So by that, you are eliminating or removing the carbon-carbon double bond. And when the carbon-carbon double bond is removed, you have the carbon chains becoming straight. And once they become straight, these molecules tend to stick together. So it's not a good idea to hydrogenate vegetable oils and convert them to saturated fatty acids. Now, sometimes this hydrogenation process kind of rearranges the hydrogens in a way that it does not add any hydrogens, but it just straightens the chain by arranging the hydrogens on the opposite side of the carbon-carbon double bond. So now the hydrogens are balanced and therefore the chain straightens. So it is technically an unsaturated fatty acid, but because of the trans arrangement of the hydrogens, you have the kink straightened out. So it behaves just like a saturated fatty acid and is responsible for a lot of cardiovascular conditions. But the major function of fats is energy storage. This is the most compact way to store a lot of energy. And the tissue in animals that stores the fats is called the adipose tissue. And the adipose tissue is found in various regions of animals, especially the regions surrounding the vital organs, and also right under the skin, which insulates the body. Then the next category of lipids are the phospholipids. Phospholipids are the most important lipids because they, like I mentioned earlier, they form the membrane of living cells. And these look very similar, the phospholipids look very similar to the fatty acid or the triglycerides, in that they also have a glycerol molecule. And this time, instead of 3 fatty acid chains, you have 2 fatty acid chains. And the third one is replaced by a phosphate group. And the phosphate group always has a negative charge, which gives a part of this molecule, phospholipid molecule, hydrophilic properties. Okay, so this part of the phospholipid molecule is able to bind to the water molecules, whereas the fatty acid chains are still hydrophobic. So this is kind of like somewhat soluble in water, but it's not truly soluble in water. Like say, if you put salt in water, it would just disappear. You wouldn't see that in the phospholipids, which is a good thing because this would be the perfect candidate or the perfect molecule to make any membrane, because cells are surrounded by water and they also have mostly water inside. So there has to be an arrangement that separates the cell from the surrounding. So this is what it looks like. There's the phosphate group, that's the glycerol, and then you have the 2 fatty acids. Now, the fatty acids can be both hydrophobic, both unsaturated or both saturated. It just depends on the type of fatty acids that are incorporated with glycerol. And this is how we usually draw the fatty acid, phospholipid. You have the phosphate head, which is hydrophilic, and the lipid tails, or the fatty acid tails, that are hydrophobic. So this is what a membrane looks like under electron microscope. So it is basically a series of these phospholipids that are arranged side to side. And then another such layer is arranged, but it's flipped. It's kind of like a mirror image. So this is called the bilayer, phospholipid bilayer. It has 2 layers of phospholipids. And this is what every living membrane, biological membrane, looks like, whether you're talking about the nuclear membrane, the plasma membrane, the membrane around a mitochondria. Any membrane you could possibly think of has this structure. Now, why is the structure important? Like I said earlier, you have water on the outside, water on the inside. Right? So if you had water on the outside and inside, and the phosphate heads are hydrophilic, so they would just dissolve in the water. But you want a plasma membrane that separates the inside from the outside of the cell. And that's what these tails do. They are fats, they are hydrophobic, they do not dissolve in water, and therefore now you have a layer that separates the inside of the cell from the outside of the cell. And at the same time, these tails do not shy away from water because they are attached to the phosphate heads, which can bind with water and keep this membrane in place.
The structure of a phospholipid. Phospholipids are essential for a cell because they form the membranes that delineate the cell's boundaries and internal compartments. In an aqueous environment, phospholipids, each shown here as a small cartoon symbol, self-assemble into a double layer to form a membrane. This mere double layer of phospholipids separates 2 aqueous compartments, such as the inside and outside of a cell. Let's look at how the structure of phospholipids causes them to form a double layer when put in water. Just like in a fat molecule, the central structure of a phospholipid is a 3-carbon glycerol with a chemical group attached to each of its 3 hydroxyls. In a fat molecule, all 3 hydroxyls are attached to fatty acids, but in a phospholipid, only 2 are attached to fatty acids, which form the tails of the molecule. Notice that if the fatty acid has a cis double bond, this will cause a kink in its shape. The remaining hydroxyl of the glycerol is attached to a phosphate group, which is why these are called phospholipids. In a typical cellular environment, the phosphate will carry a negative charge. The phosphate may in turn be attached to another small polar or charged molecule. In this example, the phosphate is joined to a positively charged choline molecule, so we call this particular phospholipid phosphatidylcholine. These groups make up the head of the phospholipid. In this space-filling model of a phospholipid molecule, you can see its overall shape, including the 2 fatty acid tails, made of a skeleton of carbons, shown in black, with the attached hydrogens, shown in gray, and the head of the molecule, which contains carbon and hydrogen, plus oxygens, shown in red, phosphorus, shown in yellow, and nitrogen, shown in blue. Now let's think about how the different parts of the phospholipid interact with water. Which part of the molecule has affinity for water, the head or the tails? Recall that water is a polar molecule, so the head of the phospholipid molecule, which has attached charged and/or polar groups, has an affinity for water. In other words, the head is hydrophilic. The fatty acid tails at the other end of the molecule are nonpolar and hydrophobic, so they won't interact with water. If phospholipids are added to an aqueous solution, the hydrophilic heads will interact easily with the water molecules, but the hydrophobic tails will be excluded from the water. The tails will end up getting pushed together away from the water molecules, and the heads will be facing toward the water. Eventually, they'll assemble into a double-layered sheet called a bilayer, with water on both sides of it. The bilayer has the hydrophobic tails sandwiched between the hydrophilic heads. The phospholipid bilayer is the fundamental structure of biological membranes. Note that the phospholipids are not chemically bonded to each other in the bilayer, they're just assembled together due to the hydrophilic and hydrophobic interactions with the surrounding water. For simplicity, figures in the book represent the phospholipids in a bilayer as identical cartoon molecules, but in reality, there are many different variations of phospholipids. Given what you know about the basic structure of a phospholipid, what parts do you think could be modified to create variant phospholipids? Phospholipids can have many variant structures because there are many different fatty acids that can make up the tails, combined with many different small molecules that can attach to the phosphate on the head. This chemical variation in structure results in different functions and allows the various membranes to carry out the variety of membrane functions required to sustain life.
The last group of lipids we're going to be talking about are the steroids. Steroids are also bulky molecules, and they are made of fused rings, 4 fused rings. And cholesterol is an example of a steroid, and it is usually the precursor, or this is the base using which several other steroids are synthesized in animal cells. And cholesterol is also found in the plasma membrane of animal cells. There are both low density and high density cholesterol, and the low density is the one that may lead to cardiovascular diseases. So this is the structure of a cholesterol molecule. It's a very complex, bulky molecule, and having these cholesterol molecules in the plasma membrane help the plasma membrane maintain its fluid-like nature or fluidity, because you don't want the plasma membrane to be a rigid barrier, but it should be kind of semi-permeable, or it should allow certain substances to move in and out. So having a bulky molecule among those predominantly phospholipids in the plasma membrane, it maintains the fluid-like nature of the plasma membrane. Okay, the third group of macromolecules we're going to be talking about are the proteins. Proteins are considered the tools using which the cells perform all the functions that they perform, such as defense, storage, transport, cellular communication, movement, and structural support. So they perform pretty much all the functions that any living cell performs, and they make up about 50% of the dry mass of all cells. And here it shows the various functions with examples of the various categories of proteins. So some proteins are used as enzymes. Enzymes are basically catalysts. They speed up a chemical reaction. So Enzymes are biological molecules. They are made most of the time by your body or by the cells, and they help speed up the biochemical reactions, such as, say, digestion. So we have a whole bunch of enzymes that help break down our food into smaller monomers or individual monomers so that our body can absorb the nutrients better. So this process would happen even in the absence of enzymes, but then it would take forever. But using the enzymes, we can speed up the process several fold. And then the next one is the defense proteins. Defense proteins, for example, are the antigens and the antibodies in your body. So these are constantly looking out for any foreign cells or foreign proteins, such as, say, a viral particle or a bacterial cell, and they attack that protein or cell and mark it for destruction. So antibodies are usually found in the liquid part of the cell, and the antigens are usually on the surface of the blood cells. So they play a very important role, which is defense. The other one is storage. There are several storage proteins. So proteins also have a lot of energy, and they are used basically for providing energy as well as for providing amino acids, which are the building blocks for all the other proteins in an organism. So eggs that contain albumin, that is an example. So they provide amino acids required for the embryo to develop. And casein, which is the protein found in the milk, is also considered a storage protein. Transport proteins are usually located on membranes, whether it is the plasma membrane, the nuclear membrane, endoplasmic reticulum. So these are kind of like gates through which some molecules enter or exit the cell. Hormonal proteins are another class of proteins, and hormones are primarily used in maintaining the rate of metabolism in organisms, primarily in animals. For example, insulin, it helps with the glucose metabolism. It helps regulate the glucose levels in the blood. So, for example, if we consume a meal that is rich in starch, insulin is secreted by the pancreas into the bloodstream, which then makes the liver cells and the muscle cells pick up that excess glucose and convert it to glycogen and store it. Remember, glycogen is our storage polysaccharide. So by this process, what happens is the blood glucose level comes back to normal. So in a way, this is helping with the homeostasis, which is basically maintaining a steady or a constant internal environment. And the next one is the receptor proteins. Since we are multicellular organisms, or for that matter, any multicellular organism, the communication between cells is very, very important so that they are all on the same page when it comes to a certain process. Then how do these cells communicate? They communicate by exchanging molecules, chemical molecules. So here you see how there are these little red dots. Those are the signal molecules. So there is a neuron that is giving off these signal molecules. Let's say, for example, a neurotransmitter. And this cell here is the one that receives, and it responds to that signal. Now, how does it receive, or how does it even recognize that signal? It has special proteins on the surface of the plasma membrane. So these little purple cup-like things here, those are the receptors, and they are a perfect match for the signaling molecule. So it's, again, there has to be a perfect match between the signal and the receptor. Only then the cell will respond to that signal. So here, the recipient cell is picking up the signals with the help of the receptor, and then based on what the signal is, the cell responds accordingly. Okay. And that's how all the processes happen in cells, especially when you have multicellular organisms. Cell communication is very, very important. And then the next one is a contractile and motor proteins. These are proteins that help with the movement, like the muscle proteins. Muscle proteins, there are primarily two proteins that help with the movement of the muscle tissue, actin and myosin. And both of these proteins are arranged as alternate fibers. As you can see here in alternate layers, you have actin, myosin, actin, and then you would have another myosin layer and so on. And so when what causes the movement, whether you're moving your hands, you're blinking your eyes, or your heart beating, or walking around, or your breathing movements, the food moving through the digestive tract, all of these are a result of muscle movements. So these two layers of actin and myosin slide over each other, and that is responsible for the contraction of the muscles, which results eventually in the movement. And the last one is the structural proteins, which provide support to either a tissue or to cells or an organism or even an organ. So here, for example, we see two different types. One is a keratin, another one is collagen. They're both structural proteins, especially the collagen protein is unique to animals. And since animals do not have cell walls, these protein molecules, the collagen fibers, provide the support that a cell wall would for a cell. So the collagen fibers help attach or hold all the cells of a tissue together. So that way they provide the support. And keratin is a protein that is found in the hair, nails, feathers, and then horns, and also there's silk fibers in the spiders, cocoons. All of these are made primarily of keratin that provide structural support.
Proteins, represented as purple blobs in this close-up of an animal cell, are the most complicated molecules known. A cell contains thousands of kinds of proteins, which carry out a variety of functions. In most cases, a protein's function depends on its complex three-dimensional structure. Let's see a demonstration of each of the protein molecules shown here and learn about its function. Observe how function depends on protein shape and changes in shape. Structural proteins have many functions. Like tent poles and ropes, they shape cells and anchor cell parts. They may serve as tracks along which cell parts can move. They bind cells together, making organized units such as muscles, ligaments, and the tendons that bind muscles to bones. The silk of spiders and the hair of mammals are also structural proteins. Signal proteins include hormonal proteins that help coordinate an organism's activities by acting as signals between cells. For example, insulin, a hormonal protein secreted by the pancreas, signals an animal's cells to take in sugar. The hormone receptor is also a protein. Signal molecules bind to receptor proteins that can then relay messages inside a cell. Receptors are thus important links in the system of communication among cells. Some signal molecules are also proteins. Transport proteins carry molecules from place to place. The example shown here allows certain solute molecules to enter the cell. Hemoglobin is the transport protein that carries oxygen in the blood. Sensory proteins detect environmental changes such as light and respond by emitting or producing signals that call for a response. An enzyme is a protein that changes the rate of a chemical reaction without itself being changed into a different molecule in the process. Enzymes promote and regulate virtually all chemical reactions in cells. Storage proteins stockpile building components that cells can use to make other proteins. Storage proteins in seeds provide raw materials used by the developing plant, unless an animal eats them first. Ovalbumin, the main substance in egg white, serves as a storage protein for developing chick embryos. Contractile proteins, like the motor protein shown here, can move parts of a cell. Other contractile proteins, working together in muscle cells, can move a whole animal. Gene regulatory proteins bind to DNA in particular locations and control whether or not certain genes will be read. This allows cells to become specialized for different functions and respond to changes in their surroundings. The immune system makes defensive proteins called antibodies that bind to invaders, such as the virus shown here, and mark the foreign objects for destruction.
Okay, so all proteins are made of polypeptides, and proteins are folded in various levels, but proteins are all polymers, and they are made of monomers known as amino acids. So amino acids would be the monomers for proteins. So during dehydration reactions, amino acids are joined together to build a polypeptide. Okay? And this polypeptide is then processed, folded in various levels to make a functional protein. And these amino acids are joined by covalent bonds, and here the name of the covalent bond that is found between amino acids is called the peptide bond. So amino acids are 20 in number in total. So there are 20 amino acids, and the name amino acid indicates that it has two very important functional groups. One is the amino group, which is NH2, and the other one is the carboxyl group, which is the acidic group. And so every one of the 20 amino acids has a very similar structure. It has a central carbon, okay? And it has an amino group, a carboxyl group, a hydrogen. So everything in purple. Now these are the list of 20 amino acids. Now if you notice, all of the purple shaded areas for all the 20 amino acids is identical. Then how do we have 20 different amino acids? So the part where the fourth bond is formed, now every carbon forms 4 bonds. Now this is the central carbon. This is the central carbon. How do we identify the central carbon? The carbon that is attached to the amino on one side, carboxyl on the other side, is the central carbon, also known as the alpha carbon. And then it also has a hydrogen. So these are the 3 bonds that the central carbon is forming. The fourth bond is attached to various different structures or groups of atoms. So this, we just give it a generic term called as the R group. We call this the R group. It is kind of like a placeholder again. So this R group could be anything. So all these different colored ones that you see here, the yellow, the green, the pink, and the blue, these highlighted regions are the R groups, which form the fourth bond with the central alpha carbon. Now, the properties of these amino acids vary based on the R group. There are some that are nonpolar amino acids. Now, how can you say these are nonpolar? Because they predominantly have nonpolar covalent bonds like CH3. So anytime there is carbon and hydrogen involved, it's going to be nonpolar. And then you have polar side chain amino acids, the ones in green. Now, how do we know these are polar? Because you have an OH. Anytime you have atoms that have completely different electronegativity, such as those of oxygen and hydrogen, they are going to eventually form a polar covalent bond. And same thing, you have an OH here, and then you have an SH. We also, in chapter 2, we said sulfur belongs to the same family as oxygen, so it's going to behave pretty much like oxygen. Then OH, NH2, N is also nitrogen, is another atom that has a pretty high electronegativity. And then CO. All of these tend to make the R group or the R side chain polar. And then you have some that are acidic and some that are basic. The R groups are acidic. How do we know this is acidic? That's because, see, this COOH. So this was OH, and the H is released. And by definition, any molecule that gives off hydrogen ions is an acid. And here, the NH2 has picked up a hydrogen ion and has become NH3+. So that is the property of a base. A base is a substance that picks up hydrogen ions, right? So that's what makes these 20 amino acids different and unique. And these amino acids are linked by covalent bonds, and we have a special name for them. It's called the peptide bonds. And there could be several hundreds or thousands of amino acids in a polypeptide. And every polypeptide chain has 2 ends, the C terminus and the N terminus. Let's take a look at that. So here you have a short chain of amino acids, just 2 amino acids. And then you have the third amino acid coming in. Now, remember the very first generic dehydration reaction that we saw with the little circles, right? That looks like a string of pearls. It's the same thing, but here we're talking about the dehydration reaction in context of the proteins, how a polypeptide is made, right? So you're just extending this polypeptide chain by adding a third amino acid. And this is a dehydration reaction. See how the water molecule is removed, and as a result of that, there is this peptide bond formed that now joins the last amino acid in the chain and then the newest amino acid that has been added, right? So now the polypeptide chain is 3 amino acids long. Now, this is a short chain of polypeptides, and you have the N terminus, N because it has the amino group or the nitrogen, and this is the C terminus, which has the COOH or the carboxyl end. And this carboxyl end is the end where you can add more amino acids. So this is the direction in which this polypeptide chain is going to grow. Also, a polypeptide chain has 2 distinct regions. One is called the backbone, which comprises of the central carbon, the carboxyl groups, and the amino groups. And then you have the R groups forming the side chain. Okay, so that's the side chain of all the amino acids.
Life depends on proteins. These large molecules make up almost all the structures of a cell and mediate most all of its functions. Proteins are responsible for just about everything you do. For instance, enzymes are proteins that catalyze and regulate all the chemical reactions of your body. Other proteins, called transport proteins, move molecules into and out of your cells across the cell membrane. Some proteins act as signaling molecules that bind to protein receptors on cells and help to coordinate your body's activities. For example, the hormone insulin is a signal that causes cells to take up glucose. And the contractile proteins that make up your muscles let you dance. How can proteins perform these and so many other functions? What can you observe about the differences between these proteins? Right, they obviously differ in shape. A protein's function depends on its specific shape. Let's explore how that shape arises. A protein is made from amino acids joined by peptide bonds to form a polypeptide. The proteins of your body are composed of 20 different amino acids. You can see the different kinds indicated here by their 3-letter abbreviations. Let's take a closer look at the makeup of an individual amino acid. Each amino acid has an amino group, a carboxyl group, a hydrogen atom, and a variable group symbolized by R, and all are attached to a central carbon atom. The R groups of the various amino acids differ in their size and composition. An R group can be hydrophobic, meaning water-fearing, or hydrophilic, meaning water-loving. These properties help determine what shape a protein assumes. Note that leucine's R group is nonpolar and thus hydrophobic. Hydrophilic R groups may be polar, as shown here with serine, or even charged, as you can see in aspartic acid. So let's build a protein. The final functional shape of a protein is based on several superimposed levels of structure: primary, secondary, tertiary, and in many, but not all proteins, quaternary. Primary structure is the sequence of amino acids. This specific sequence is determined by instructions written in a cell's DNA. Added levels of structure, however, are required to turn a linear string of amino acids into the functional shape of a protein. There are 2 types of secondary structures. Portions of the chain may coil into an alpha helix. Other segments may fold back and forth, forming beta-pleated sheets. These secondary structures are held together by hydrogen bonds, shown here as dotted lines between hydrogen and oxygen atoms of the polypeptide backbone. You can see secondary structures compacted in the globular 3-dimensional shape of this polypeptide. The overall shape of a protein is called its tertiary structure. This shape results from interactions between R groups of the various amino acids. Hydrophobic R groups cluster in the center of a protein, out of contact with water. R groups that have positive or negative charges may form ionic bonds. Hydrogen bonds can connect polar R groups, and covalent bonds may form between sulfur-containing R groups. These disulfide bridges reinforce the shape of some proteins. You just learned that various types of interactions between the amino acids that make up a polypeptide chain produce the secondary and tertiary structures that determine a protein's shape. But can changes in the chemical or physical environment disrupt a protein's shape and thus its function? For example, could an increase in temperature or a change in acidity affect a protein? Yes, a physical or chemical change in the protein's environment may disrupt the chemical interactions responsible for secondary and tertiary structure, causing the protein to unravel. This process is called denaturation, Without its specific shape, a denatured protein loses its function. Many proteins consist of a single polypeptide, and thus have just primary, secondary, and tertiary structure. But some proteins have a quaternary structure, in which 2 or more polypeptide chains are aggregated into one functional protein, such as transthyretin, as seen here. In summary, a protein's functional shape results from 4 levels of structure: primary, secondary, tertiary, and sometimes quaternary.
As you saw in the little video, the embedded video, a protein or a polypeptide has to be folded at various levels to become a functional protein. And so what is made at the end of protein synthesis or at the end of gene expression is basically the primary structure, which is nothing but a polypeptide or a chain of amino acids, right? So this is not the functional protein yet. It is just a string of pearls. So this primary structure has to then go through the secondary structure, and the bonds that hold the secondary structure are hydrogen bonds. So the hydrogen bonds are responsible for forming the secondary structure. For the primary structure, it's the peptide bonds. Remember, we talked about how the amino acids are joined by covalent bonds, also known as the peptide bonds. And the secondary structure, hydrogen bonds. So these bonds are very, very important. You should know what bond is responsible for each of these protein structures. And then the tertiary structure is determined by the interactions between the R groups. So the R groups, remember, if you go back to the slide that has the short amino acid chain, you will see that the amino acid chain or the polypeptide is divided into 2 regions. One is the backbone structure, which has the amino group, the carboxyl group, the central alpha carbon, and the hydrogen. And then you have the side chain, which is basically a combination of all the R groups, right? So the tertiary structure is formed by the interactions of all these R groups. So eventually it's going to, now the R groups are several kinds. We talked about the various types of amino acids based on the nature of the R group. So if the R group is acidic or basic or hydrophobic, hydrophilic, you saw in the video how different types of bonds are possible, such as ionic bond or a covalent bond or hydrogen bond or hydrophobic interaction. So all of these are possible at the tertiary level. And most proteins are functional at the tertiary level. There are some proteins that have to go through the next level, which is called as the quaternary level. And this is nothing but a combination of various tertiary structures put together. Again, the type of chemical bonds involved could be any type of chemical bonds known. So these are the 4. Now, example of a quaternary structure would be hemoglobin, where you have 4 tertiary structures joined together to make a functional hemoglobin molecule. Same thing with collagen. Collagen is a structural protein in animals, and that is also a result of 3 tertiary structures put together. So I'm just going to skip through these slides because we did talk about all of this information. So that's the primary structure. You can see how the chain of amino acids, right? And then you have the carboxyl end, the amino end. And this is where the carboxyl end is where you can add more amino acids. Then the secondary structure, the hydrogen bonds are responsible. So you have a repeated structure like, say, the pleats or a helix or a coil. Okay, so this is a coil, right? And this is kind of like a beta pleated structure, like folds. So all of these are just repeating structures formed because of hydrogen bonds. And then the tertiary structure, all kinds of bonds are possible. We saw this in the video as well. That's the hydrogen bond between the polar R groups, hydrophobic interactions between hydrophobic R groups, and then a covalent bond, also known as a disulfide bridge, and then ionic bond between the acidic and the basic groups. And here's the example of collagen, which is a quaternary structure made of 3 tertiary structures. The same thing goes for hemoglobin. You have 1, 2, 3, 4 tertiary structures put together to form a functional hemoglobin molecule. So this is just an example to show how important the structure of a protein is to be able to function normally. So sickle cell disease is the result of a change in the primary structure. Now, how is the primary structure changed? The primary structure is a result of the instructions in the DNA or in the gene. So if there is a change in the DNA, that is reflected most of the time as a change in the amino acid. Now, we saw how the tertiary structure is formed. It's formed because of the interactions between the R groups. So if you switch the amino acid, let's say you switched a polar amino acid to a non-polar amino acid, that is a 180 degrees switch, right? A complete opposite of what they're supposed to be, right? So this could be a result of a mutation or a change in the DNA. So an amino acid is switched, and because the amino acid is now completely different with different properties, different bonding, and different interactions with the other amino acids, the protein folding pattern is going to be different. And when the protein folding pattern is different, the ultimate protein that is made is also going to look different. Right? It will end up with a different shape. And at the very beginning in chapter 2, we said the structure of a molecule is the key to its normal function. And so now when the structure of the protein is altered, the function is also altered or it does not happen. Right? Like say, for example, here in sickle cell. Now, this is the chain of amino acids or the primary structure. There is amino acid number 6 that is switched. And this switch has resulted in an altered structure of the beta subunit of hemoglobin. It has this little dent. And so it's going to interact with the alpha subunits differently now. And so it's going to form a slightly different structure with these dents, and see how those dents result in a different kind of, like, all of these stick together. Whereas here you have these separate. Right? Now, when these stick together, they form these rod-like structures. And when you have such hemoglobin molecules packed inside red blood cells, look at the shape of the red blood cells. It is altered. It has a completely different shape, like a sickle or a crescent. Right? And this is the normal shape. It's a disc-shaped cell. And that would result when you have normal shaped hemoglobin. But when you have this abnormal shape, this causes the sticking of individual hemoglobin molecules, giving it an elongated structure, which is reflected in the as a change in the cellular structure, the red blood cells. So when you have when the red blood cells are of this shape is not the perfect shape for the cells to squeeze through microscopic capillaries. So what happens is insufficient oxygen, insufficient nutrients are supplied to various regions of the body. And that results in weakness, fatigue, persistent fatigue. And the only fix for this is to treat the symptoms or to transfuse healthy red blood cells into the patient. But the permanent cure would be only if the gene is fixed. So besides the genetic factor, besides the gene, what other conditions, what other factors determine the structure or of the protein? There could be several environmental factors such as the pH or salt concentration, which means ion concentration because salts are made of ions. And then temperature. These are some of the factors that could alter the shape of a protein. So a protein that has lost its normal shape because of these environmental factors is called as denaturation. So the process is called as denaturation, and the protein is known as a denatured protein. It's almost like, say, you take eggs and cook them. So you're heating them. So you're increasing the temperature. So what happens there is the tertiary structures open up. The secondary structures open up because the heat breaks the hydrogen bonds. Right? So when the hydrogen bonds break, the secondary structure is lost. So they just unravel, they open up, and their shape is altered. And that's the difference. And most of the time, this denaturation is permanent. Like when you cool down the temperature after you cook eggs, it does not go back to the liquid form, like egg albumin. It does not go back to that state. So that's a permanent denaturation. Right? But in the living cells, when something like this happens, like a protein denatures, sometimes you have the special proteins, other special proteins that renature or put the protein back to the normal shape. That's called renaturation. So that in rare cases that happens, and most of the times it is the blood proteins that go through this renaturation process. Okay, and sometimes when the protein structure goes through alteration, it leads to various conditions such as Alzheimer's or Parkinson's, mad cow disease. All of these are a result of a misfolded protein. Okay, now the last group of macromolecules we're going to be talking about are the nucleic acids. Nucleic acids are primarily DNA and RNA. We also consider ATP, the energy currency, as one of the nucleic acids as well. So nucleic acids, they are basically, we talked about how amino acid sequence is built. It is based on what information is present in the gene, right? And the genes are nothing but DNA, right? And DNA is a nucleic acid. DNA stands for deoxyribonucleic acid. Okay. And the other molecule is RNA, also known as ribonucleic acid. Now, when DNA, and out of these two, DNA is considered as the master molecule because it has all the information that the cell needs to make every other molecule, such as, say, RNA. There are so many different types of RNAs. Every one of these RNAs is made using the information on the DNA or in the genes. And also all the proteins of a cell are made using the information on the DNA. Okay. So this process of using the information in the genes and making a protein or any other molecule such as mRNA or tRNA, rRNA, that's called as gene expression. Okay. So this is what gene expression in eukaryotes looks like. And the reason I'm calling this eukaryote is because there is a nucleus, right? Prokaryotes do not have a nucleus. So here you see the first step where the information on the DNA is copied onto an mRNA. So if you consider DNA as a book of recipes, a page as one of the genes, the information on that page is copied onto another nucleic acid called as mRNA. And now this is just the copy of the recipe to make a certain protein. So this mRNA synthesis, which is the first step, it's called as transcription. So this mRNA then moves into the cytoplasm and it is held by a ribosome, and a tRNA then reads the information. Remember, the recipe or the instructions to make a protein are now copied onto this mRNA. And so now we have the information on the mRNA, and this mRNA information is read and is translated into a polypeptide, which is the primary structure. So this process of using the information or translating the information on an mRNA to make a polypeptide is called as translation. So this is the direction of the flow of information, that from DNA to RNA and RNA to a protein.
Moving towards the nucleus, we pass by layers of internal membranes. The nucleus is enclosed by a double membrane called the nuclear envelope. Let's enter the nucleus through a pore. The nucleus houses the genetic material of the cell, DNA, which carries the blueprints for making the cell's proteins. Almost 2 meters of DNA is crammed inside the nucleus. How does it all fit? The DNA is wrapped around proteins like thread wrapped around spools. Look, this section of the DNA has unwound, and a different protein has attached to the DNA. DNA is being used as a template to make mRNA. mRNA molecules travel from the nucleus to the cytoplasm, carrying the instructions for making specific proteins. In the cytoplasm, a ribosome clamps onto a strand of mRNA. The ribosome ratchets along the mRNA, building a new protein. Some proteins stay in the cytoplasm. Others, like this one, are processed in special compartments within the cell.
Okay, so the nucleic acids, that is DNA and RNA, are again polymers. They are all polymers, and they are made of individual repeating units called as nucleotides. So a chain of nucleotides or a polymer of nucleotides is also known as a polynucleotide, right? And each nucleotide or each building block is actually a combination of 3 different components. One is a nitrogenous base, then you have a pentose sugar, that is a 5-carbon sugar, and it has a phosphate group. Now, coming to the nitrogenous bases are divided into 2 groups: pyrimidines, which are the C for cytosine, T for thymine, and uracil or U is found only in the RNA. DNA has thymine instead of uracil. And then you have purines, which are the other 2 nitrogenous bases, that is adenine and guanine. Right? So you have a total of 5 different nitrogenous bases. So you take one of these and then either a deoxyribose sugar, which is the 5-carbon sugar, in which case it would become a DNA nucleotide, or a ribose sugar, in which case the nucleotide would be an RNA. Okay? And then you finally add a phosphate group. Okay? So notice how this is one nucleotide. This is the nitrogenous base. This is the 5-carbon sugar. And then this is the phosphate group. So these units keep repeating. That's the phosphate, that's a 5-carbon, that's a nitrogenous. Phosphate, 5-carbon, nitrogenous, and so on. So that is the repeating unit. And see how there are numbers on these carbons, the first carbon, second, and then the third, fourth, and then the fifth. So those are called as the prime, 1 prime, 2 prime, 3 prime. 3 prime is the one that has the OH, which means that's the one that is going to interact with the next nucleotide coming in, and the chain will grow a little longer. So basically the 3 prime end is the open end, or this is the end that can be used to add more nucleotides and elongate this DNA or RNA for that matter. And then the 5 prime end is always the dead end. It's the closed end. It has, so the 5th carbon always has the phosphate group, and that cannot interact or that cannot add a nucleotide. Okay, so that is considered as the closed end. Okay, so the individual nucleotides are joined by covalent bonds called as phosphodiester linkage. So this is the name of the covalent bond given to the in the nucleotides or the polynucleotides or nucleic acids. So these are the bonds you need to remember, the bonds that hold the individual monomers together. In the carbohydrates, it's called the glycosidic linkage. In the proteins, it's called the peptide bond. In the nucleic acids, it's called a phosphodiester linkage. Okay. And also the DNA is double-stranded. It's also called as the double helix because it has 2 strands of the polynucleotide, and each of these goes in opposite direction, right? So I'll show you what it looks like. So this arrangement is called antiparallel arrangement, where you have the 2 strands of the DNA molecule running in opposite directions. Okay. And also you have these 2 strands that are held together by hydrogen bonds. Now, what nucleotides form hydrogen bonds? Always. This is called the base pairing rule. So the adenine or the A always pairs up with the T via 2 hydrogen bonds. And the guanine always pairs up with the cytosine with 3 hydrogen bonds. So this is called as a complementary base pairing. And in the RNA, if the DNA is pairing up with RNA during the transcription process, you would have the U pairing up with an A. So DNA is always a double-stranded molecule. It looks like a rope ladder that is twisted over itself. And see how the direction of the strands is the opposite. And that arrangement is called as antiparallel arrangement. And then you have these hydrogen bonds. So DNA is always double-stranded and RNA is always single-stranded. Sometimes, yes, it does fold over itself and form these hydrogen bonds, but RNA is considered single-stranded, DNA double-stranded. Okay, so that brings us to the end of this chapter. The next 3 slides, it's just a summary of the the 4 groups of macromolecules with examples and their corresponding functions. So make sure you go over these 3 slides at the end as well. So that's the lipids, and then you have the proteins, and finally nucleic acids. Okay, and that's the end of this chapter 5, or macromolecules. I'll see you in the next chapter.